Hey guys, tonight we're going to stand on the edge of the deepest canyon in the world, but it's not a canyon of rock, it's a canyon of time. We're journeying to a place so far in the past that the very continents themselves are strangers, to ask a question so huge it can make your head spin. What if we weren't the first? Imagine, we are at the south rim of the Grand Canyon. Before you lies one of the most profound sights on Earth. The sun is setting, painting the vast chasm in shades of orange, red, and deep purple. Each distinct layer of rock stacked below you isn't just a different color, it's a different chapter in the planet's autobiography. A page from a book 1 billion years in the making. Now, look down at your feet, at the soil and the thin layer of rock you're standing on. That topmost layer, that dusty, barely there veneer at the very peak, that's everything. That's all of human history. The pyramids, the Great Wall of China, every empire, every war, every song ever sung. It all fits in that single, insignificant layer. Over the next little while we are going to journey down into that canyon, past the age of mammals, deeper than the bones of the last dinosaur, beyond the first flower that ever bloomed. We will descend through seas of red rock into a time so ancient and alien it might as well be another planet, a world that existed right here, beneath our feet, but is now lost to time. And as we descend, we'll be searching. So what if one of those thick, ancient layers holds the story of another? A civilization that rose, built, dreamed, and then fell, vanishing so completely that the only thing left of them is a strange stain in the rock. How would we even begin to look for such a thing? What clues would they have left behind? Thanks to a new way of thinking, a new kind of geological detective work, tonight we will venture into these depths together to find the answers. Frankly, if you were dropped into some of these ancient time periods without a special suit, you wouldn't survive a single second to realize where you went wrong. The air itself would be poison. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. It always fascinates me to see where you're all tuning in from. Let me know in the comments where you are in the world and what time it is for you. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. That view from the canyon rim does something to your sense of time. It makes you feel small, temporary. It's a feeling that geologists have been grappling with for centuries. Before the late 1700s, most of Western civilization thought the Earth was only about 6,000 years old, a tidy little history that started not long before the first human records. But a Scottish farmer and physician named James Hutton, often called the father of modern geology, looked at the rocks and saw a story that was violently, unimaginably longer. He saw layers that had been deposited as sand at the bottom of an ocean, then compressed into stone, then tilted vertically by some immense force, then eroded flat, only to have new horizontal layers of sediment deposited on top of them. He realized that these processes were so slow that for all this to have happened, the Earth couldn't be thousands of years old. It had to be ancient beyond all human reckoning. He wrote that he could see no vestige of a beginning, no prospect of an end. This concept is what we now call deep time. To manage this abyss, Geologists have organized Earth's history into a formal timescale, a cosmic calendar of our planet. The largest divisions are eons, which are broken into eras, then periods, then epochs. We are currently in the Phanerozoic eon, the Cenozoic era, the Quaternary period, and the Holocene epoch. It sounds as complicated, but it's just a way of naming the chapters in that Grand Canyon book. The story we're looking for, the one about a civilization before the dinosaurs, would be filed away deep in the Paleozoic era, a time that ended 250 million years ago. The tools to read this book are incredibly clever. You can't just count the layers like rings on a tree. The key is radiometric dating. You've probably heard of carbon-14 dating, which is great for things that were alive in the last 50,000 years or so. But for deep time, scientists use other elements, like uranium trapped in tiny zircon crystals. Uranium-238 decays into lead-206 at a very precise, very slow rate. By measuring the ratio of uranium to lead in one of these crystals, a scientist can calculate its age with incredible accuracy. It's this technique that tells us the rock at the bottom of the Grand Canyon is nearly 2 billion years old, and that the Earth itself is 4.54 billion years old. It's our planetary birth certificate. But even with these tools, there are mysteries. There are missing pages. Right there in the Grand Canyon, you can find a stark line in the rock called the Great Unconformity. Below this line, you have tilted ancient rock from 1.7 billion years ago. Right on top of it, you have flat, younger rock from just 500 million years ago. That means there's a gap. Over 1 billion years of Earth's history is just gone, wiped from the record. Geologists still argue whether this was caused by a massive period of erosion from glaciers that scoured the continent down to its roots, or by some other complex tectonic process. Whatever the cause, it's a chilling reminder of just how easily this planet can erase its own past. If 1 billion years of rock can vanish, what chance would a city, or even a whole civilization, have? That billion-year gap in the rock is unsettling, isn't it? It's like trying to read a history book with most of the chapters ripped out. It forces you to confront the true scale of what came before us. So, let's try to get a better grip on that scale. You are a Homo sapiens, an anatomically modern human. Our species has been walking the Earth for about 300,000 years. That sounds like a long time, and it is. It's long enough for ice ages to come and go, for continents to drift slightly, for entire cultures to rise and be forgotten. But when you place that 300,000-year history against the 4.5 billion-year history of the planet, it shrinks to almost nothing. It's a rounding error. It's 0.006% of the total story. To make it feel more real, let's use that classic analogy and compress all of Earth's history into a single calendar year. On this scale, the Earth forms on January 1st. The first, simplest forms of life, just single-celled organisms, don't appear until late March. The Cambrian explosion you may have heard of, that sudden riot of complex animal life we saw in the deeper parts of the canyon, doesn't happen until mid-November. The dinosaurs, they show up around December 15th and have a great run, dominating the planet until a very bad day on December 26th. So where are we in all this? The first ancestors who could be called human don't appear until the evening of December 31st. Your species, Homo sapiens, emerges into the world at about 11:54 p.m. The whole of recorded human history, every pyramid, every poem, every king and queen, takes place in the final 14 seconds before midnight. The Roman Empire, in this calendar, lasts for about 5 seconds. The United States has existed for just over 1 second. Think about the oldest city you can. Maybe you think of Rome or Athens. But the oldest continuously inhabited city we know of is Byblos, in modern-day Lebanon. People have lived there for around 7,000 years, which is an incredible testament to human endurance. But that city, a place that has witnessed the birth of writing and the rise and fall of countless empires, is built on rock that is hundreds of millions of years old. Its entire 7,000-year history is just a thin layer of dust on a much, much older foundation. Now consider our own footprint, the mark our global civilization is making. Our industrial revolution, the moment we really started to alter the planet on a grand scale by burning fossil fuels, is only about 250 years old. In our cosmic calendar, that's the last half second before the New Year's bell chimes. The age of plastics, the material that now infests every corner of the globe, from the deepest ocean trench to the peak of Mount Everest? That's less than 100 years old. A tiny fraction of a second. Our digital age, the world of computers and the internet that feels so all-encompassing, has only truly existed for about 30 years. That's the final flash of the firework at midnight. We feel like masters of this planet, but we are brand new, and our technology is even newer. This realization has led some scientists to think about what kind of mark we'll actually leave in the geological record. This is the quirky and slightly unnerving concept of technofossils. Millions of years from now, what will be the telltale signs of our existence? Future geologists might find a strange stratum of rock containing bizarre, unnatural materials. They might find the compressed and fossilized remains of our sprawling cities, a distinct layer of concrete, steel, and glass. They could find fossilized plastic bottles and bags, or maybe even the ghostly imprints of billions of CDs and DVDs, their rainbow sheen still faintly visible in the stone. These technofossils would be an undeniable signature, a clear sign that something very different, something artificial, existed during this brief moment in time. This idea is the basis for a proposed new geological epoch, the Anthropocene, or the Age of Humans. The evidence for it is overwhelming. We have fundamentally altered the planet's chemistry, geology, and biology. We've doubled the amount of fixed nitrogen in the environment thanks to our fertilizers. We've spread aluminum, a metal that is almost never found in its pure form in nature, across the entire globe. And of course, we've pumped so much carbon dioxide into the atmosphere that we have reversed a 50-million-year-long cooling trend. We are, without a doubt, a geological force. Yet scientists are still debating the official starting date for the Anthropocene, with some suggesting the beginning of the Industrial Revolution in the late 18th century, and others arguing for the Great Acceleration of the 1950s, marked by the distinct radioactive fallout from the first atomic bomb detonations. That fallout created a global signature, a thin layer of artificial radioisotopes that will be detectable for hundreds of thousands of years. It's a somber thought that the clearest, most permanent marker of our arrival might be the invention of our own potential self-destruction. So we're leaving behind a clear signature in the rock, a layer of technofossils and chemical ghosts that will shout our existence to the far future. But for how long? It's easy to think of the Earth as a passive stage, a solid, permanent library where each layer of rock is a book filed away and kept safe forever. But that isn't true. Our planet is not a library. It's a living, breathing, self-cleaning machine. It is an active and sometimes violent system that is constantly working to erase its own surface, recycling its crust, and wiping its own memory clean. The most powerful of these erasing mechanisms is plate tectonics. You're probably familiar with the basic idea. The Earth's crust isn't one solid shell. It's broken up into a dozen or so major tectonic plates that float and grind against each other on the semi-molten mantle below. In some places, like the mid-Atlantic ridge, plates are pulling apart. Magma rises from the mantle to fill the gap, creating brand new ocean floor. This is the Earth's creative process. But because the planet isn't getting any bigger, for every bit of new crust that's made, an equal amount has to be destroyed somewhere else. This happens at what are called subduction zones. These are places where one plate, typically a dense oceanic plate, is forced to dive beneath another, less dense continental plate. Imagine a colossal, world-spanning conveyor belt. New seafloor is born in the fire of a mid-ocean ridge. Then it spends millions of years traveling across the ocean basin, collecting sediment and the history of the life and death that rains down upon it from above. But eventually, it reaches the end of the line. At the subduction zone, it plunges back down into the Earth's mantle, where the immense heat and pressure melt it back into the primordial rock it came from. Its entire history, every fossil, every chemical trace, every layer of sediment, is completely and utterly erased. This process is relentless, and it means that the Earth's oceans are geologically very young. The vast majority of the ocean floor on the entire planet is less than 200 million years old. Think about what that means for our search. If an advanced civilization existed, say 300 million years ago, and it had built gleaming cities along its coastlines, or magnificent structures on its continental shelves, or even vast habitats on the ocean floor itself, the very ground they built on would now be gone. It would have been dragged down into the mantle and melted into oblivion. There would be nothing left to find. We are searching for a library where the head librarian is a pyromaniac, constantly burning the oldest and most interesting books. You don't even need to wait millions of years to see geology swallow up history. Look at the famous ancient city of Alexandria in Egypt. Founded by Alexander the Great, it was home to the Great Library and the Lighthouse of Alexandria, one of the wonders of the ancient world. But due to a combination of earthquakes and the slow sinking of the land, known as subsidence, a huge portion of the ancient city, including the royal quarters where Cleopatra herself lived, is now underwater in the harbor. Divers can swim among the sphinxes and fallen columns of a lost world that was thriving just 2,000 years ago. Geology can work fast. The forces that drag the old world down are balanced by forces that lift new land up. For a truly mind-bending, quirky fact, consider the highest point on our planet, the summit of Mount Everest. The rock at the very peak, nearly 9,000 meters above sea level, is not volcanic rock as you might expect. It is marine limestone, filled with the fossilized fragments of tiny sea creatures. This means that the rock that forms the roof of the world was once at the bottom of an ancient sea, the Tethys Sea. It was lifted to its incredible height by the slow, unstoppable collision of the Indian and Eurasian tectonic plates. The planet is a geological elevator, constantly moving floors up and down. And the process is happening right now, beneath your feet. The scientific evidence is undeniable. Using GPS and other satellite measurements, we can watch the continents move in real time. The plate you're on is likely moving at a rate of a few centimeters per year, about the same speed that your fingernails grow. It seems impossibly slow, but over the course of 100 million years, That slow crawl adds up to thousands of kilometers. Cities become mountain ranges, and continents are rearranged like furniture in a room. While the general theory of plate tectonics is settled science, geophysicists continue to debate the exact mechanisms that initiated plate tectonics on the early Earth. We don't fully understand how or when this planetary recycling engine first switched on, but we know that once it did, it became the primary force shaping our world, and the primary force erasing the deep past from the record. Any civilization that came before would have had to contend with a world that was actively trying to bury them. Plate tectonics is the great, slow conveyor belt to oblivion, wiping the slate clean over hundreds of millions of years. But even if a civilization's homeland managed to survive that continental-scale recycling, it would still have to contend with a more persistent and intimate form of destruction: the simple, patient work of the wind and the rain. This is erosion, the second great eraser. It's a quieter force than the grinding of continents, but it is just as relentless. It's the planet's way of sanding itself smooth. Imagine you are standing on a newly formed mountain range, all sharp peaks and jagged cliffs. From the moment it is born, the mountain is dying. Water, the universal solvent, gets into tiny cracks in the rock. When it freezes, it expands, wedging the cracks wider. This is called frost shattering. Day after day, year after year, this process repeats, turning solid rock into gravel. Rainwater, which is naturally slightly acidic, slowly dissolves the very minerals that hold the rock together. Rivers, armed with the sand and silt they carry, act like liquid sandpaper, carving deep canyons and gorges. Glaciers, those immense rivers of ice, scour entire valleys, grinding mountains down into dust. And the wind, a gentle breeze to you, becomes a tireless sculptor over millennia, sand-blasting rock faces into strange and beautiful shapes. Now place a city in the path of these forces. Imagine a sprawling metropolis like New York or London, suddenly abandoned. For the first few hundred years, it would be a battle between nature and steel. Plants would be the first invaders. Ivy would crawl up skyscrapers, its tendrils forcing their way into mortar and concrete. Tree roots would buckle sidewalks and tear apart foundations. Without maintenance, water would get everywhere, rusting the steel skeletons of the buildings from the inside out. Within 1,000 years, most buildings would be precarious ruins, green mounds of rubble. After 10,000 years, the relentless action of water, ice, and plant life would have ground most of the city down to its foundations. After 100,000 years, a passing ice age could scrape the entire site clean, leaving behind little more than a smear of crushed concrete and rusted metal in the glacial debris. And after a few million years, the very memory of the city would be nothing more than a slightly unusual layer of compressed rock, deep underground. The only way to beat this process is to be buried, and buried fast. The famous Roman city of Pompeii is the perfect example. In 79 AD, Mount Vesuvius erupted, burying Pompeii and the nearby town of Herculaneum in a thick blanket of hot ash and pumice. This was a horrific tragedy for the people who lived there, but it was a miracle for archaeology. The ash layer protected the city from the forces of erosion. It froze a moment in time, preserving buildings, mosaics, and even the hollow spaces left by the bodies of the victims. Pompeii is a historical treasure precisely because its preservation was so unnatural. It's the exception that proves the rule. For every one city that is flash fossilized by a volcano, Thousands of others are simply left to rot and crumble into dust. Most of history doesn't get a protective blanket of ash. It just gets washed away by the rain. You can see smaller, spookier examples of this burial process in what are called ghost forests. Along some coastlines, you can walk among the dead, grey stumps of ancient trees standing in the salt water of a tidal marsh. These were once healthy forests, growing on dry land. But due to a sudden earthquake that dropped the land's elevation, or a rapid rise in sea level, the forest was drowned by the invading ocean. The salt water killed the trees, but the waterlogged, oxygen-poor sediment preserved their stumps for thousands of years. A ghost forest is a stark, beautiful memorial to a landscape that was suddenly and violently buried. The rate at which this burial happens is called the sedimentation rate, and it's the key scientific evidence for understanding preservation. In some places, like a quiet lake bottom or a deep sea floor, sediment builds up incredibly slowly, maybe just a millimeter every 1,000 years. In other places, like a river delta during a flood, you can get meters of new mud deposited in a single day. To have any hope of being preserved, the remains of a civilization would need to be in a location with a high rate of sedimentation. They'd need to be buried in a geological blink of an eye. Scholars still debate the precise erosion rates of ancient mountain ranges, trying to understand how fast the landscape changed in the deep past. But the conclusion is always the same. On geological timescales, the surface of the Earth is a surprisingly fluid and temporary thing. For our hypothetical pre-dinosaur civilization, this means they couldn't have just built their cities anywhere. To leave a trace, they would have needed to be in the right place at the right time, and then have the incredible geological luck of being flash-buried instead of slowly erased. So the planet's geology is actively working against us. It's melting continents and grinding down mountains, erasing the vast majority of the physical stage. Any evidence of cities or structures would likely be long gone. But what about the inhabitants themselves? What about their bodies? Couldn't we find the fossilized remains of the citizens of this lost world? This brings us to the third great filter of preservation, and it's perhaps the most difficult one to pass. Becoming a fossil is not the default outcome for life on Earth. It is a staggering miracle of chance. It's like winning a lottery against odds so high you can barely write the number down. Think about what normally happens when an organism dies. Whether it's a plant, an animal, or you, the process of decay begins almost immediately. Scavengers arrive to tear it apart. Bacteria and fungi get to work, breaking down the soft tissues. The bones might last a little longer, but they too are eventually weathered by the sun and rain, gnawed on by animals for their calcium, and ultimately turned to dust. 99.999% of all life that has ever existed on this planet simply vanishes, recycled back into the ecosystem without a trace. To win the fossilization lottery, you have to bypass all of that. First, you have to die in the right place. Not on a dry plain or a mountainside where you'll erode away, but somewhere like the bottom of a lake, in a quiet swamp, or on the floor of the sea. Second, you have to be buried, and just like with a city, it has to happen quickly. A layer of mud, sand, or volcanic ash must cover your remains, sealing them off from the oxygen and the scavengers that would tear them apart. This is the crucial step. Third, you have to stay buried. Your geological resting place must be stable, not one that gets subducted into the mantle or crushed by tectonic forces. Finally, the magic happens. Over thousands and millions of years, water seeps down through the sediment and into your bones. This water is rich in dissolved minerals. like silica or calcite. Very slowly, molecule by molecule, these minerals begin to replace the original organic material of your bones. It's a process of substitution, creating a perfect stone copy of the original. This is a fossil. It's not bone anymore. It's rock in the shape of a bone. It's an echo, a ghost in the stone that has survived the immense journey through deep time. Given this incredibly specific and unlikely chain of events, you can see why the fossil record is so incomplete. The scientific evidence is stark. Paleontologists estimate that far less than 1%, some say less than 0.1%, of all species that have ever lived are known to us through their fossils. That number is worth pausing on. It means that for every one fossil species we have discovered, there are at least 1,000, maybe 10,000, others that lived and died and vanished completely. Entire ecosystems, teeming with life, have existed and disappeared from the record as if they were never there. If whole branches of the tree of life can be lost, the odds of finding a fossil of one specific, intelligent species from 300 million years ago become almost vanishingly small. It wasn't until the early 1800s that we even knew such creatures existed. A self-taught paleontologist and fossil collector in England named Mary Anning made a series of incredible discoveries, including the first complete skeleton of an ichthyosaurus, a dolphin-like marine reptile from the age of dinosaurs. People were stunned. This was not a creature that existed anywhere on Earth. It was an animal from another world, a lost world. Anning's discoveries were crucial scientific proof of the concept of extinction, opening up the radical idea that the planet's history was filled with creatures that were long gone. The fossil record is so full of gaps that it even has a term for creatures that seem to come back from the dead. These are called Lazarus taxa, named after the biblical figure Lazarus, whom Jesus resurrected. A Lazarus taxon is a species that vanishes from the fossil record, is presumed extinct for millions of years, and then suddenly reappears in much younger rock layers. The most famous example is the coelacanth, a bizarre-looking fish that was thought to have died out with the dinosaurs 66 million years ago, until a living one was caught by a fisherman off the coast of South Africa in 1938. The coelacanth hadn't gone extinct. It had just been lucky enough to live in environments where it didn't win the fossilization lottery for 66 million years straight. This quirky tidbit perfectly illustrates the problem. If we can lose track of an entire order of fish for that long, how could we ever be certain that an intelligent, land-dwelling species wasn't just hiding in one of the fossil record's many gaps? These gaps are most profound at the very beginning of complex life. Paleontologists argue about whether the Cambrian explosion was a genuine, rapid diversification of life, or simply the period when organisms first evolved hard parts, making them suddenly visible in the fossil record. For hundreds of millions of years before the Cambrian, life was soft-bodied. It was an entire world of worms, jellyfish, and microbial mats that left almost no trace. It's possible that intelligent life could have evolved then, but if it had no bones, no shells, no hard parts to fossilize, we would likely never, ever know. So the deck is stacked against us. The planet melts and grinds down the evidence of structures. The very process of fossilization is so rare that entire species can vanish from the record. If we go looking for a lost civilization by trying to find a fossilized radio telescope or the crushed remains of a stone library, we are almost certainly doomed to fail. The odds are just too astronomical. It seems like a dead end. But what if we've been looking for the wrong thing all along? What if, instead of searching for a needle in a continent-sized haystack, we should be looking for evidence that the entire haystack is somehow different. This is the brilliant and compelling core of a thought experiment proposed in 2018 by astrophysicist Adam Frank and NASA climatologist Gavin Schmidt. They called it the Silurian Hypothesis. Now, for a quick and quirky bit of context, the name doesn't come from a deep scientific principle. They named it after an old episode of the TV show Doctor Who, which featured an ancient race of intelligent reptiles called the Silurians, who went into hibernation millions of years ago. It's a playful name for a very serious idea. Frank and Schmidt weren't saying they believed in a lost race of lizard people. They were approaching the problem as scientists. They asked a simple, powerful question. If an industrial civilization like our own had existed on Earth many millions of years ago, what testable scientific signatures would it have left behind in the geological record? This question completely changes our approach. We stop being paleontologists looking for a unique bone. We become planetary forensic investigators. Imagine you arrive at a crime scene. The culprit is long gone, and they didn't leave behind any obvious clues like a wallet or a set of keys. So, what do you look for? You look for the subtle traces they left behind. You look for fingerprints on a doorknob, trace amounts of chemicals on the carpet, a strange footprint in the mud outside. You look for the impact the culprit had on their environment. The Silurian Hypothesis proposes that we do the same thing with the planet. We stop looking for the civilization's wallet and start looking for its fingerprints all over the geological record. We have a perfect historical example of this kind of detective work, solving a massive planetary mystery. For decades, scientists debated why the dinosaurs went extinct. Then, in 1980, the father-son team of Luis and Walter Alvarez discovered something extraordinary. At sites all around the world, they found a thin layer of clay that precisely marked the 66-million-year-old boundary between the Cretaceous period and the Tertiary period, the exact moment the dinosaurs vanished. And in this clay, they found shockingly high levels of the element iridium. Iridium is very rare on the Earth's surface, but is much more common in asteroids and comets. This iridium layer was the smoking gun. It was the forensic evidence, the planetary fingerprint of a massive asteroid impact. It proved that the reign of the dinosaurs ended in a cataclysm from the sky. We didn't need to find a fossilized dinosaur with a piece of asteroid embedded in it. The proof was in the global chemical trace the event left behind. This is the kind of evidence we should be looking for, not a fossilized city, but a chemical scar running through the rock strata. And the most obvious signature an industrial civilization like ours would leave is in the planet's carbon cycle. Our entire global economy is built on burning fossil fuels, coal, oil, and natural gas that were formed from the buried remains of ancient life. When we burn them, we release enormous quantities of carbon dioxide into the atmosphere. But crucially, the carbon from these ancient plants is isotopically different from the carbon that's normally in the atmosphere. Plants prefer to use the lighter isotope of carbon, carbon-12, over the slightly heavier carbon-13. So, when we burn billions of tons of ancient plant matter, we flood the atmosphere with an unnaturally high amount of carbon-12. This shift in the ratio of carbon-12 to carbon-13 gets recorded everywhere. It's in the ice cores, it's in the shells of tiny marine organisms that sink to the ocean floor, and it gets locked into the layers of sedimentary rock. A future geologist, millions of years from now, will see a sharp, dramatic spike in the carbon-12 ratio right at our point in history. It's called a carbon isotope excursion, and it's the primary, undeniable fingerprint of our industrial civilization's effect on the planet. So, The first question the Silurian Hypothesis asks is this: can we find other, unexplained carbon isotope excursions deep in the Earth's past? Could one of them be the signature of a forgotten industrial age? The investigation has now truly begun. A sudden spike of light carbon in the rock is a tantalizing clue, a potential sign that someone was burning through a lot of ancient forests or coal beds. But it's not definitive proof. A massive, prolonged period of natural volcanic activity could, in theory, produce a similar, though likely less abrupt, signal. To build a stronger case, a planetary detective needs more than one type of evidence. You need to find multiple independent lines of inquiry, all pointing to the same culprit: industry. The Silurian Hypothesis, therefore, proposes looking for other, more specific fingerprints that are harder to explain away with natural causes. Let's consider the second major signature we are creating: plastics and other synthetic pollutants. Our modern world is quite literally built on these materials. Look around you right now, and you will undoubtedly see dozens of things made of plastic. It is a miracle material, cheap, durable, and versatile. But its greatest strength, its durability, is also its greatest curse. Plastic doesn't biodegrade like wood or paper. Instead, it just breaks down into smaller and smaller pieces. A plastic bottle tossed into the ocean will be battered by waves and bleached by the sun. It will crumble into tiny fragments, then into microscopic particles known as microplastics. You've likely heard of the Great Pacific Garbage Patch, a floating gyre of plastic debris, larger than the state of Texas. But that's just the stuff we can see. The real problem is the trillions of invisible microplastic particles suspended in the water column and settling on the ocean floor. This plastic dust is now a permanent part of the planet's sedimentary cycle. It is raining down on the abyssal plains and being buried in the mud. Millions of years from now, this will form a distinct, unnatural layer in the rock, a stratum filled with complex, durable hydrocarbon molecules that nature, on its own, would never create. Finding a similar layer of bizarre, complex organic molecules in a 300-million-year-old rock bed would be an electrifying discovery. It would be a powerful piece of evidence for a civilization that had mastered polymer chemistry. Next, consider a third signature, one that comes from the way we feed ourselves. To support a global population of 8 billion people, we rely on industrial-scale agriculture, which in turn relies on artificial fertilizers. For most of Earth's history, the amount of fixed nitrogen available for plants to use was limited. But in the early 20th century, scientists developed the Haber-Bosch process, a method for pulling nitrogen directly from the air and converting it into ammonia for fertilizers. It has been called the most important invention of the 20th century, responsible for feeding billions who would have otherwise starved. But it has also flooded the planet's ecosystems with massive amounts of reactive nitrogen, leaving a distinct isotopic signature in the soil and water. A sudden dramatic shift in nitrogen isotopes in the rock record would be another strange signal. It would suggest that someone had figured out how to bypass one of life's fundamental chemical limitations. We have clear historical precedent for industry leaving such global chemical traces. For much of the 20th century, most of the gasoline we used contained lead. The exhaust from countless cars released this heavy metal into the atmosphere, where it circulated around the globe and eventually settled everywhere. Scientists drilling into the Greenland ice sheet have found a distinct layer of lead contamination that peaks in the 1970s and then declines as unleaded gasoline was phased in. This is a perfect example of a specific industrial process, leaving a clear, global, and datable chemical fingerprint. To search for these ancient fingerprints, scientists rely on one of their most powerful tools: sediment and ice cores. They can drill deep into the ocean floor or into a polar ice cap and pull out a long cylinder of material. This core is a beautiful high-resolution history book. Each layer represents a specific period of time. By analyzing the chemistry of each layer, scientists can reconstruct past climates, see the ash from distant volcanic eruptions, and detect shifts in atmospheric composition. This is how we know what the Earth's climate was like hundreds of thousands of years ago. And it's within these cores, these delicate layers of mud and ice, that we might find the subtle chemical whispers of a lost world. Of course, the planet can sometimes create surprising things on its own. For a truly quirky tidbit, look to Oklo in Gabon, Africa. There, you can find the remains of a naturally occurring nuclear reactor. About 1.7 billion years ago, a deposit of uranium ore had a high enough concentration of uranium-235 and was flooded with groundwater in just the right way that it spontaneously initiated a sustained nuclear fission reaction. It ran in pulses for hundreds of thousands of years. While entirely natural, the Oklo reactor proves that nuclear signatures can be preserved in the rock. Finding a similar signature, but with isotopes of plutonium or other elements that don't occur in nature, would be perhaps the most conclusive and terrifying piece of evidence of all. It would be the fingerprint of a civilization that had, for better or worse, unlocked the power of the atom. We have our forensic toolkit. We know the kinds of subtle, planetary-scale fingerprints an industrial civilization might leave behind. A strange blip in the carbon cycle. A layer of molecular ghosts that look like plastic. A whisper of industrial metals. Or even the faint echo of nuclear fission. We are no longer searching for a single bone or a ruined temple, but for a global chemical scar. Now, with this new set of eyes, it is time to begin our journey. It's time to leave our familiar world behind and travel back into the deep, alien past. Set your time machine. We are bypassing the Cenozoic era, our own age of mammals. We are flying past the entire Mesozoic era, the 180 million year reign of the dinosaurs. We are going deeper, to a time before the first dinosaur ever walked the earth, before the first flower ever bloomed. We are setting our destination for the Paleozoic era, a vast stretch of time that lasted from 541 to 252 million years ago. This is the era of ancient life, and it is here, in this truly primordial world, that we will begin our search. Let's land in the first period of the Paleozoic, the Cambrian. You step out of your time machine, and the world is almost unrecognizable. The air is thin and has a strange metallic smell. The scientific evidence tells us that the atmospheric oxygen levels are much lower than today, perhaps only around 12% compared to our comfortable 21%. You'd need a breathing apparatus to survive here. The sun in the sky looks slightly smaller and dimmer, as stars naturally increase in brightness over their long lives. Look up at night, and the moon appears huge, looming much larger in the sky than you're used to. It was significantly closer to the Earth back then, and its gravitational pull would have created immense, powerful tides that swept across the shorelines. And there is a lot of shoreline. The continents are not in their familiar positions. There is no Atlantic Ocean. Most of the planet's landmass is fused together into a giant supercontinent called Gondwana, with a few smaller continents scattered about. This means most of the planet is a single, globe-spanning ocean, and there is no life on the land. Not a single tree, Not a blade of grass, not even any moss on the bare, rocky shores. The land is silent, sterile, and alien. But the ocean is a different story. Here, life is exploding in a frenzy of evolutionary creativity known as the Cambrian explosion. You wade into the warm, shallow water, and you are surrounded by creatures straight out of a bizarre science fiction film. Scuttling along the seafloor are the trilobites, arthropods in ornate armored shells. These creatures are the icons of the Paleozoic, and for a quirky but important bit of perspective, they were one of the most successful animal groups of all time, surviving for almost 300 million years. To put that in perspective, our own species, Homo sapiens, has so far only managed about 0.1% of that time. You see a creature that looks like a flattened, swimming centipede with 5 mushroom-like eyes on stalks and a long, flexible trunk that ends in a grasping claw. This is Opabinia. Swimming nearby is the apex predator of this world, Anomalous, a 2-foot-long creature with 2 large, spiky appendages for seizing prey, and a strange, square-shaped mouth that looks like a pineapple ring lined with teeth. Nothing here has a familiar body plan. Evolution is experimenting, trying out every conceivable design before settling on the ones that would last. Our understanding of this bizarre menagerie comes from one of the most important fossil discoveries ever made. In 1909, the paleontologist Charles Walcott discovered the Burgess Shale, a fossil bed high in the Canadian Rockies. This site contained not just the hard shells of trilobites, but the exquisitely preserved, ghostly impressions of the soft bodies of all these other strange creatures. It was like finding a complete photograph of an alien ecosystem. Without the Burgess Shale, this entire chapter in the Book of Life would be a mystery to us. So, you stand in this ancient Cambrian world, a world of low oxygen, a bigger moon, and seas teeming with alien life. Could a civilization have existed here? It seems unlikely. Life was complex, but it had not yet developed the kind of large brains or manipulative limbs that would seem to be a prerequisite for tool use and technology. The raw ingredients are here, but they are still being mixed. The Cambrian was a riot of creation, but perhaps too chaotic, too new for the slow, steady evolution of intelligence to take hold. We must continue our journey forward in time, deeper into the Paleozoic, to a world that is about to change in a very dramatic way. The Cambrian world, with its bizarre sea creatures, was a critical first draft of complex life, but the land remained a barren, empty desert of rock. As we move our time machine forward, past the Ordovician period, with its great diversification of marine life, we enter the Silurian, and then the Devonian periods, roughly 440 to 360 million years ago. And it is here that one of the most profound events in the planet's history begins. The world is about to turn green. You are standing once again on that sterile, rocky shoreline. But now, something is different. Clinging to the damp rocks at the water's edge are patches of green. These are the first true pioneers of the land, small moss-like plants. For hundreds of millions of years, life had been confined to the oceans, but these humble plants are the vanguard of an invasion. They are followed by the first tiny land animals, creatures that look like mites and primitive wingless insects, venturing out of the water to feed on the decomposing plant matter. The beachhead has been established. As we move forward into the Devonian, this green frontier expands with astonishing speed. The key innovation is the evolution of vascular tissue, specialized cells that can transport water and nutrients. This is like the invention of plumbing for plants, and it allows them to grow upright, away from the immediate safety of the water's edge. At first, they are just small, stick-like plants like Cooksonia, but soon they evolve into dense, shrubby thickets, and then into the planet's very first forests. You walk into one of these Devonian forests, and it feels both familiar and deeply alien. The air is humid and smells of damp earth and decay. There are tree-sized plants all around you, but there are no flowers. There are no birds singing in the branches. The silence is broken only by the hum of primitive insects and the scuttling of scorpion-like arthropods in the leaf litter. The trees themselves are strange. For a quirky tidbit, the first truly tree-like plants, such as Archaeopteris, didn't have broad leaves like a modern oak, but feathery, fern-like fronds. And they didn't reproduce with seeds, but by releasing clouds of primitive spores, just as ferns and fungi do today. This was a world of shade and spores. Our detailed knowledge of this first terrestrial ecosystem comes from another miraculous fossil site. The Rhynie Chert, located in a field in Scotland, is a 410 million-year-old slice of a Devonian hot spring environment. It was flash fossilized by silica-rich water, preserving the plants and tiny arthropods in exquisite, microscopic detail. It's like a perfect diorama, showing us the very moment the land came to life. Meanwhile, back in the oceans, life has become a ferocious arms race. This is the age of fishes. The seas are now ruled by a terrifying new kind of predator. You look down into the water and see a Dunkleosteus, a creature the size of a large great white shark, but covered in a thick, bony armor plating. It has no teeth in the way we think of them. Instead, its jaws are two massive, self-sharpening, bony plates that could shear through any prey with terrifying force. The trilobites are still around, but they are now a secondary act to these new vertebrate kings. And it is from these fish that the next great leap is about to be made. In the shallow, swampy waters, a new kind of lobe-finned fish evolves. One of them, a creature we now call Tiktaalik, has a flattened, crocodile-like skull and fins that contain the primitive bone structure of a wrist and fingers. It could do something no fish had done before. It could prop itself up on its fins in the shallows, and perhaps even pull itself out of the water for brief periods. This was the ancestor of all land-dwelling vertebrates. You, in your own body, carry the legacy of this creature's strange, modified fins. This is a pivotal moment, the beginning of the vertebrate conquest of the land. This greening of the continents wasn't just a backdrop for evolution, it was a powerful engine of global change. The scientific evidence is clear. As these first great forests spread across the globe, they began to have a dramatic impact on the atmosphere. Plants breathe in carbon dioxide for photosynthesis. The sheer biomass of these new forests acted like a planetary-scale CO2 scrubber, pulling enormous quantities of this greenhouse gas out of the atmosphere. The result was a period of global cooling, a reverse greenhouse effect. This climate shift was so severe that it is believed to have been a major cause of the late Devonian mass extinction, an event that devastated marine ecosystems. The irony is stark. The triumph of life on land led to a catastrophe in the seas. It's a sobering reminder that even natural biological processes can destabilize a planet's climate if they happen too quickly. The world is becoming more complex, more interconnected, and perhaps more suitable for a complex intelligence to finally emerge. The Devonian forests gave the land its first breath of life, a world of green ferns and primitive trees. But now we move forward into the next great chapter of the Paleozoic, the period that will serve as the primary stage for our thought experiment. We are entering the Carboniferous period, which lasted from roughly 359 to 299 million years ago. The name itself is a clue to its importance. It comes from the Latin for coal-bearing, and it is here that the planet's environment becomes truly supercharged, creating a world that seems almost designed for gigantism, a perfect incubator for a strange new form of life to take hold. You step out of the time machine, and the air is immediately different. It feels thick, heavy, and incredibly humid, like the inside of a supercharged greenhouse. You take a breath, and it feels richer, almost effervescent. The scientific evidence from gas bubbles trapped in ancient amber and other geological markers is clear. During the Carboniferous, atmospheric oxygen levels soared to astonishing heights, reaching as high as 35% compared to our modern 21%. This oxygen-rich air has profound consequences for life. It supercharges metabolism, allowing creatures to grow larger and become more active. It also makes the air much denser, which would make it easier for flying creatures to stay aloft. You are standing in the midst of a vast, continent-spanning swamp forest. The ground is a soggy, tangled mess of roots and fallen logs. The trees are bizarre. Towering over you are scale trees, like lepidodendron, which aren't true trees in the modern sense. Their trunks are covered in a diamond-like pattern of leaf scars, and instead of branching like an oak, they fork perfectly in two, over and over again. Giant horsetails, looking like colossal versions of the little weeds you might find by a pond, grow to the size of modern pines. The entire landscape is a monotonous, humid, and shadowy world of greens and browns, stretching as far as the eye can see. But it's the inhabitants of this swamp that truly define the era. The high oxygen levels have had a dramatic effect on arthropods, the creatures with exoskeletons like insects and spiders. Because they breathe through tiny tubes in their bodies, their size is normally limited by how much oxygen can diffuse through these tubes. But in the Carboniferous, this limitation is lifted. You hear a loud buzzing sound and look up to see a dragonfly, Meganeura, with the wingspan of a modern eagle, soaring through the thick air. Scuttling through the undergrowth is Arthropods, a millipede-like creature over 2 meters long and half a meter wide, armored like a tank. In the stagnant, soupy water of the swamp, giant amphibians, some the size of crocodiles, lie in wait. This is a world of monsters, a planet on steroids. One of the most crucial and quirky facts about this period is what happened when all these giant plants died. Today, when a tree falls in a forest, it is quickly broken down by a host of bacteria and fungi that have evolved to digest tough plant materials like lignin and cellulose. But back in the Carboniferous, this microbial toolkit was still in its infancy. The specific fungi and bacteria that could efficiently rot wood had not yet evolved. So, when these giant scale trees and ferns died and fell into the swamp, they didn't fully decompose. They just sat there, piling up layer after layer, a colossal accumulation of dead organic matter. This is a historical fact of immense importance, one that directly connects this ancient world to our own. Over millions of years, this undecayed plant matter was buried by sediment. The immense pressure and heat from the Earth's crust slowly cooked and compressed it, driving off water and other elements, leaving behind pure, energy-rich carbon. This is the origin of the great coal seams of Europe, Asia, and North America. The electricity that is powering your home right now may very well be coming from the fossilized remains of one of these strange carboniferous forests. Our entire industrial revolution, the very foundation of our modern world, was built by burning the ghosts of this ancient age. This unique combination of factors, the high oxygen, the giant life forms, the peculiar biochemistry that led to the preservation of so much organic energy, makes the Carboniferous the perfect setting for a hypothetical civilization to arise. Paleobotanists still debate the precise combination of atmospheric conditions and evolutionary factors that allowed for the gigantism of Carboniferous arthropods. But whatever the cause, it created a world teeming with energy and biological potential. Here, in these endless humid swamps, among the giant insects and primitive trees, we have all the raw materials needed. We have a stable, energy-rich environment and a host of large, complex creatures. This is the most promising landscape we have yet encountered on our journey. It is from this world that our candidate for Earth's first civilization will emerge. We have found our stage. The Carboniferous period, with its oxygen-rich air, its colossal swamp forests and its giant arthropods, is the perfect crucible for a non-human intelligence to be forged. The vertebrate amphibians are still clumsy, tied to the water, their brains small and primitive. But the arthropods, they have ruled this planet for over 100 million years. They are diverse, adaptable, and in this era, they are giants. It is from this lineage that we will draw our candidate for Earth's first technological species. Let's give them a name. We'll call them the geodes, not because they are made of rock, but because their civilization, like a geode, is a hidden world of wonders contained within a plain exterior. Let's imagine the geodes evolved from a creature like the giant millipede Arthropleura. But instead of being solitary scavengers, they developed a sophisticated social structure, much like modern termites or ants. They became eusocial. This is the key. It means that most individuals in a colony are sterile workers, dedicating their lives to the collective good, all in service to a queen or a small group of reproductive elites. This structure allows for a level of cooperation and specialization that is impossible for individualistic creatures like us. A single geode is not intelligent in the way you are. It is a relatively simple, instinct-driven creature. The true intelligence of the geodes is collective. It's a hive mind. Their consciousness is not located in a single brain, but is an emergent property of the entire colony, a network of millions of individuals working in perfect concert. They are not a civilization of people. They are a civilization that is itself a single continent-spanning superorganism. Their communication is completely alien to us. You stand in the Carboniferous swamp, and the world seems silent. But for them, it is a deafening symphony of information. They communicate primarily through chemistry. They release complex pheromones from specialized glands, creating a chemical language of incredible subtlety and precision. They can leave trails that tell their nestmates not just where to find food, but what kind of food it is, how fresh it is, and what dangers lie along the path. Their antennae twitch, tasting the air, reading the chemical stories left by others. They also communicate through vibrations, tapping their limbs on the ground in complex rhythms, sending messages through the substrate for miles. To a geode, the world is not a world of sights and sounds, but one of tastes, smells, and rhythms. Anatomically, they are masters of specialization. Within a single geode colony, you would find dozens of different castes, each one biologically engineered for a specific task. There are the foragers, with long, sensitive antennae and powerful legs for traversing the forest floor. There are the soldiers, massive brutes with heavily armored exoskeletons and powerful mandibles capable of slicing through the giant amphibians of the era. There are the diggers, with shovel-like heads and short, strong limbs for expanding their vast underground networks. And there are the tenders, delicate, nimble creatures who cultivate the colony's food and care for the young. Their senses are finely tuned to their world. Their compound eyes are not great at seeing details at a distance, but they are incredibly sensitive to motion and can see polarized light, allowing them to navigate with pinpoint accuracy even on cloudy days. But their primary sense, the one that truly defines their reality, is their sense of smell, or more accurately, chemoreception. They can detect and identify molecules at concentrations thousands of times lower than our best scientific instruments. The air, to them, is a rich tapestry of information, a constant stream of data about the world around them. So what evolutionary pressure would drive this eusocial arthropod to develop such a powerful collective intelligence? The Carboniferous world was a paradise, but it was also incredibly dangerous. Predation from giant amphibians and other massive arthropods was a constant threat. A solitary creature would be an easy meal, but a coordinated colony, a hive mind that can think and plan, can mount a formidable defense. Furthermore, managing their food source would require immense cognitive power. Let's imagine the geodes are not just hunter-gatherers, but farmers. They cultivate vast subterranean gardens of a specific, energy-rich fungus. Maintaining the precise temperature, humidity, and chemical balance of these gardens on a massive scale would be an incredible feat of engineering and distributed data processing, a perfect problem for a hive mind to solve. The complexity of their three-dimensional subterranean world, combined with the pressures of defense and the demands of large-scale agriculture, provided the spark. Intelligence, for the geodes, was not a luxury. It was the ultimate survival tool. Having imagined the geodes into existence, let's now try to imagine what it would be like to be a geode. How does a collective consciousness perceive the world? What does society look like when the individual is secondary to the whole? This is where their civilization becomes truly alien, a concept that stretches the very definition of what it means to be intelligent. You have to erase the concept of I from your mind. For a geode worker, there is no sense of self, no personal ambition, no fear of individual death. There is only the we of the colony. Its consciousness is like a dream you're a part of but have no control over. The thoughts, the plans, the identity of the civilization doesn't reside in any single unit, but in the near instantaneous chemical and vibrational chatter between millions of them. An individual geode dying is no more significant than one of your own skin cells flaking off. It is a planned and expected loss, its biomass immediately recycled for the good of the whole. Their worldview would be one of absolute unity and purpose, a stark contrast to our own chaotic and beautiful world of competing individual desires. We can see a faint echo of this in our own world. As a historical fact, by analogy, consider the leaf-cutter ants of the tropics. These ants have one of the most complex societies on Earth outside of humanity. They don't just eat leaves, they use them as a substrate to farm a specific type of fungus, which is their sole source of food. They build colossal air-conditioned underground nests, manage waste to prevent disease, and defend their territory with a synchronized suicidal ferocity. This entire intricate operation functions without a leader giving orders. It is a decentralized, emergent intelligence. The geodes would be this concept taken to its ultimate extreme, a global colony operating with the speed and precision of a single thinking mind. With this kind of society, their technology would be fundamentally different from ours. We are tool users because we have relatively weak individual bodies. We need an external hammer because our fists are not hard enough. We need a crane because we cannot lift a steel beam. But a eusocial organism like the geodes can simply grow its own tools. Their technology would not be mechanical. It would be biological and chemical. They wouldn't mine iron ore and smelt it into steel. Why bother? They could evolve specialized worker castes that secrete chitinous armor interwoven with metallic filaments, creating a biocomposite stronger and lighter than any metal we can produce. They wouldn't build with concrete and bricks. Instead, they would grow their structures. They would manipulate the root systems of the giant carboniferous plants, guiding them into specific shapes. They would then secrete chemicals that would cause the wood to petrify, turning the living architecture into solid stone. Their cities would be a seamless fusion of biology and geology, of living and non-living matter. Their mastery of chemistry would be their defining technological trait. Think of a quirky but amazing creature from our own time, the bombardier beetle. When threatened, it can mix two chemicals in a specialized chamber in its abdomen, creating a near-boiling, noxious spray that it can aim with incredible precision. This is a simple biological chemical weapon. The geodes would have perfected this on an industrial scale. They would have castes that could produce powerful acids to dissolve rock, or secrete complex enzymes to break down plant matter into a nutritious slurry. They could create bioluminescent fungi to light their tunnels, or produce potent antibiotics to keep their colonies sterile. Their technology wouldn't be stored in factories and machines, but in the living DNA of the colony itself. What kind of speculative scientific evidence would such a civilization leave behind? The traces would be incredibly subtle, easily mistaken for natural phenomena. You wouldn't find the right-angled foundations of a ruined building. Instead, you might find a fossilized forest where all the trees are arranged in an unnaturally uniform grid pattern, the faint signature of their bioengineered architecture. You wouldn't find a garbage dump full of discarded plastic tools. Instead, you might analyze a layer of soil from the period and find bizarre chemical compositions, strange complex organic molecules, and an unusual concentration of trace elements that could only have come from the waste products of their massive underground fungal farms. These are the kinds of clues that are so easy to overlook, the whispers in the rock that the Silurian Hypothesis suggests we should be listening for. Their impact on the world would be profound, but it would look, to a casual observer, almost entirely natural. A civilization built on biological engineering and collective consciousness would not build cities in the way we do. Our cities are a product of our individuality and our physiology. We build towers that reach for the sky because we are visual creatures who thrive in the light, and we build separate structures for separate individuals or families. The geodes would have no such needs. As creatures of the forest floor, their instinct would be to go down, not up. Their cities would be vast, continent-spanning networks of tunnels, caverns, and chambers, a civilization hidden entirely beneath the surface of the great carboniferous swamps. You are standing in the humid forest, and you would see no sign of them. No roads, no buildings, no smoke. But beneath your feet, stretching for thousands of miles in every direction, is a thriving metropolis of millions upon millions of individuals. This is not a dark, crude burrow. It is a masterpiece of living architecture. The main thoroughfares are not just dug. Their walls are reinforced with a secreted, amber-like resin that is both incredibly strong and translucent, allowing the faint glow from bioluminescent fungi to illuminate the passages. The structure of the network is not a chaotic grid, but a fractal pattern, like the branches of a tree or the veins in a leaf, designed for the most efficient possible transport of individuals, air, and resources. At the heart of these subterranean networks, the geodes have harnessed the very power of the planet itself. They are masters of geothermal energy. The largest population centers, the great hubs of their civilization, are purposefully built around deep geothermal vents. They use the planet's internal heat for everything. The constant, reliable warmth is perfect for their fungal agriculture and for incubating their countless young. The steam produced by water seeping down to the hot rock is channeled through a complex system of organic pipes and valves, driving air circulation throughout the entire network. They don't have furnaces, they have tamed volcanoes. Their communication, already a symphony of chemicals and vibrations, is amplified and integrated into this network. We are only just beginning to understand the wood wide web, the quirky and fascinating network of mycorrhizal fungi that connects the roots of trees in a forest, allowing them to share nutrients and even send warning signals about insect attacks. The geodes would not just use this network. They would have engineered it on a planetary scale. They would have cultivated specific species of fungi to act as a living fiber optic network, transmitting their complex chemical messages at incredible speeds across entire continents. The thoughts of the hive mind would literally flow through the root systems of the world, a single, global consciousness embedded within the biosphere itself. We humans have, in our own primitive way, explored this subterranean world. For a compelling historical fact, consider the ancient city of Derinkuyu in the Cappadocia region of Turkey. This is a massive, multi-level underground city, carved out of the soft, volcanic rock that dates back thousands of years. It could have housed up to 20,000 people along with their livestock and food stores. It had ventilation shafts, wells, and defensive stone doors that could seal off passageways. Derinkuyu is an astonishing feat of human engineering, but it is a crude hole in the ground compared to the living, breathing, self-repairing infrastructure of the geodes. It is the difference between a mud hut and a skyscraper. What kind of geological signature would this geothermal subterranean civilization leave behind? It would be another subtle one, easily missed. Their constant and massive scale tapping of geothermal energy could have a long-term effect on the geology of the crust. It might leave behind unusual magnetic anomalies in the rock, faint scars from the redirection of heat and the movement of superheated water. Furthermore, their use of geothermally active vents would bring a constant flow of strange minerals to the surface. Their waste processing systems, likely sophisticated biological filtration beds, would concentrate these minerals. Millions of years later, this could appear as an unusual and inexplicable distribution of rare earth elements in the rock layer corresponding to their existence. It would be a chemical clue that points not just to industry, but to a very specific kind of industry, one that had learned to tap the very veins of the planet for its lifeblood. It's another fingerprint, waiting for a detective clever enough to spot it. A civilization powered by the Earth's internal heat, living in continent-spanning, the geodes have already achieved a level of success and stability that is staggering to comprehend. For millions of years, they exist in a near-perfect balance with their world. Their population grows, the hive mind expands its reach and its complexity, and their control over their subterranean environment becomes absolute. But no system can expand forever without consequences. Success itself creates new problems. The very efficiency of the geode civilization becomes its biggest challenge. Their population, the sheer number of individual units comprising the superorganism, swells to a point where even their masterful use of geothermal energy starts to reach its limits. The fungal farms, which feed the countless trillions of geodes, require more and more energy to maintain their specific temperature and chemical balance. The constant expansion and maintenance of their networks demand an ever-increasing supply of power for their biochemical synthesis. The hive mind, for the first time in its long history, is faced with a resource crisis. It needs a new source of energy, something dense, abundant, and accessible. And the solution is all around them. It is the very foundation of the carboniferous world they inhabit. Remember how the giant scale trees and ferns of this era didn't properly decompose? For millions of years, this dead plant matter has been piling up in the vast swamps, forming immense waterlogged layers of peat and proto-coal, hundreds of feet thick. To the geodes, this material is a revelation. Their hypersensitive chemical sense would analyze it and understand it for what it was, a colossal, planetary-scale battery of stored solar energy captured by plants and buried right on their doorstep. So they begin to exploit it. But the geodes would not mine coal in the way we do, with brute force excavation and destructive machinery. That would be inefficient and contrary to their nature. Instead, they would approach the problem as the master chemists they are. They would engineer specialized casts, living bioreactors, that could secrete a cocktail of powerful enzymes and chemical solvents. These worker casts would be deployed into the coal seams, where they would chemically break down the dense carbon matter into a transportable, energy-rich slurry. This slurry could then be pumped through their existing network of tunnels, a circulatory system carrying the lifeblood of their new industrial age. And they wouldn't simply burn it. Open combustion in their sealed underground cities would be a suicidal act, consuming their precious oxygen and releasing toxic gases. Again, their solution would be elegant and chemical. They would develop a form of controlled, low-temperature oxidation, or perhaps a catalytic gasification process in sealed organic chambers. This would allow them to release the stored energy of the carbon with incredible efficiency, using it to power their chemical forges, synthesize complex materials, and fuel the explosive growth of their civilization. This is the moment everything changes. This is the geode industrial revolution. It marks their transition from a planetary species living in balance with their world's energy budget to a truly geological force, one that actively alters the chemistry of the entire planet. For millions of years, the carbon from those dead plants had been safely sequestered, locked away underground. Now, the geodes have found the key and have begun to pump that ancient carbon back into the atmosphere on a massive scale. And in doing so, they create the very first piece of evidence that we, the geological detectives of the distant future, might be able to find. As they process and burn this colossal amount of ancient plant matter, they begin to release isotopically light carbon into the atmosphere. The delicate balance of carbon-12 and carbon-13 in the air and oceans begins to shift. Every shell formed by a sea creature, every layer of sediment deposited on a lake bed, every gas bubble trapped in amber, now carries the faint but indelible chemical signature of their industry. This is the birth of their Anthropocene, or perhaps more accurately, their Geode-ocene. It is the beginning of the very first carbon isotope excursion we are looking for. Before this moment, their civilization, for all its complexity and scale, was largely invisible to our methods. Its traces were subtle, local, and easily missed. But now, they have put their fingerprint on the entire planet. They have started to write their story, not just in the biological and geological landscape of the Carboniferous, but in the very air itself. A story that might just be readable 290 million years later. The discovery of fossil fuel energy unleashes a golden age for the geode civilization. With a seemingly limitless supply of power, their society undergoes an explosive expansion. The hive mind's cognitive power grows exponentially as its population swells into the quadrillions. Their subterranean networks, already vast, are expanded and perfected, burrowing deeper into the Earth's crust and spreading to every corner of the globe. This is the zenith of their power, the moment they cease to be just inhabitants of the planet and become its architects. They begin to terraform the Earth to better suit their needs. Their primary concern is stability. The great Carboniferous swamp forests are the foundation of their entire ecosystem, the source of both their food and their industrial power. They cannot allow the climate to change in a way that would threaten these forests. So, they invent large-scale weather control. Their understanding of the atmosphere is not based on physics, as ours is, but on an intuitive hive-mind grasp of chemistry and biology. They would likely release massive quantities of engineered spores or hygroscopic water-attracting chemicals into the upper atmosphere from specialized vents on the surface. These particles would act as cloud condensation nuclei, allowing the geodes to seed clouds and control rainfall patterns with incredible precision. They could ensure their beloved swamps remained wet and humid, while perhaps creating rain shadows to prevent the expansion of drier, less favorable ecosystems. With their energy and climate secured, they turn their attention to life itself. Their mastery of biotechnology reaches its peak. They don't just use the life around them, they rewrite it. This goes far beyond the simple domestication that we practice. As a form of scientific evidence by analogy, think about how humans have been genetically modifying life for thousands of years. A modern ear of corn bears little resemblance to its wild ancestor, Teosinte. A bulldog is a world away from a wolf. We have done this through slow, patient, selective breeding. The geodes, with their collective intelligence and mastery of biochemistry, would be able to do this on a molecular level, and with astonishing speed. They would engineer new forms of life as living tools. Imagine plants whose roots are designed to seek out and concentrate specific metallic ores, which the geodes could then harvest. Picture a species of fungus, designed in their bioforges that can be deployed to break down solid rock, its mycelia secreting powerful acids to carve out new tunnels for the colony. They might even create living mobile tools, specialized non-sentient biological machines designed for specific tasks like construction, defense, or even data processing. For a quirky tidbit from our own world that hints at this kind of biological partnership, look at the relationship between some species of acacia trees and the ants that live on them. The tree provides the ants with shelter in its hollow thorns and food from special nectar-producing glands. In return, the ants act as a private army, swarming and attacking any herbivore that tries to eat the tree, and even clearing away any competing plants from its base. It's a beautiful, symbiotic relationship. Now imagine a civilization that could engineer these kinds of relationships on demand for any purpose, creating an entire ecosystem of willing biological servants. The scale of their planetary engineering would be breathtaking. For a historical fact that gives us a human-scale parallel, consider the Netherlands. For nearly 1,000 years, the Dutch have engaged in a constant battle with the sea, building an elaborate system of dikes, canals, polders, and windmills. They have reclaimed huge areas of land that were once part of the ocean floor, literally manufacturing new parts of their country. It is one of the most impressive examples of human planetary engineering. But the work of the geodes would make this look like a child building a sand castle. They wouldn't just be holding back the sea. They would be managing the rain, redesigning the forests, and rewriting the very code of life to suit the needs of the hive. This world, at the height of the geode civilization, would be a paradise of efficiency and stability, a perfectly managed global garden. But in doing all this, they are creating more and more geological fingerprints. Their weather control would alter erosion patterns, leaving behind strange and anomalous sedimentary layers. Their bioengineered plants and fungi would leave behind fossilized spores and pollen of species that seem to appear in the fossil record from nowhere with no evolutionary ancestors. The world would be filled with their creations. To a future paleontologist, this sudden appearance of hundreds of new, highly specialized species would be a baffling mystery, an explosion of evolution that defied all known rules. It might, in fact, look a lot like another Cambrian explosion, but this one would be entirely artificial. For 1,000,000 years, the geode civilization exists in a state of perfect, engineered harmony. Their golden age seems eternal. They have conquered hunger, mastered their environment, and rewritten the rules of life. But in every great tragedy, the hero's greatest strength is also the source of their fatal flaw. The geode's immense success, their boundless energy, their absolute control. These very things contained the seeds of their own destruction. A paradox is taking root at the heart of their perfectly managed world. The more they control the planet, the more unstable it becomes. The first and most dangerous problem is an invisible one, a slow-building crisis in the atmosphere. Their industrial processes, particularly the massive-scale gasification of the carboniferous coal seams, are releasing colossal quantities of greenhouse gases. For a time, the vast forests of the era absorb much of this excess carbon dioxide. But the sheer scale of the geode energy enterprise eventually overwhelms the planet's natural sinks. The delicate chemical balance of the atmosphere, which the geodes had so carefully managed with their weather control systems, begins to tilt. The planet starts to warm. At first, the hive mind barely registers it. The change is a fraction of a degree over 1,000 years, a rounding error in their calculations. But it is persistent, a slow, inexorable fever. Their carefully maintained swamp forests, which require a very specific temperature and humidity range, begin to show signs of stress at their fringes. At the same time, their planetary engineering starts to generate unforeseen consequences. The hive mind is powerful, but it is not omniscient. It is managing a system of near infinite complexity, and there are feedback loops it cannot predict. Their efforts to guarantee rainfall over their primary agricultural zones in one continent lead to the creation of a persistent high-pressure system on the other side of the globe, triggering a catastrophic 1,000-year drought. Their bioengineered rock-eating fungi, designed to help them expand their tunnels, escape into the wild. There, With no natural predators, they begin to break down the surface rock at an accelerated rate, causing bizarre, large-scale landslides and altering the course of entire river systems. Their most successful engineered plant species, designed to be hyper-efficient at photosynthesis, outcompete native flora, leading to sudden, shocking collapses in biodiversity and the extinction of thousands of species that the geodes had deemed unimportant. The perfectly managed garden is starting to grow weeds, and the hive mind is forced to dedicate more and more of its cognitive power not to expansion, but to simply putting out fires. A schism begins to form within the collective consciousness itself. It's not a debate in the human sense, with shouting and arguments, but a logical conflict, a split in the data streams of the global mind. You could say that the collective memory shows a schism. One faction, a powerful thread of logic within the hive, argued for a massive, controlled retreat. Its conclusion was that the fossil fuel experiment was a mistake. They advocated for ceasing all carbon-based industrial activity, scaling back the population, and returning to a less powerful but more stable existence based on their original geothermal energy model. But another, more dominant faction argued the opposite. For this part of the hive mind, retreat was not a logical option. The only solution to the problems caused by technology was more technology and more control. They proposed a new, even more ambitious phase of planetary engineering to counteract the damage. They would build colossal, continent-spanning networks of atmospheric processes to actively scrub the excess carbon from the air. They would introduce new, even more powerful engineered species to hunt the ones that had escaped. They would double down, believing that with enough power and enough data, any system could be controlled. For a time, the more technology faction wins out. The geodes embark on a frantic new era of construction, a desperate attempt to build a machine that can manage the planet. But the system is spiraling. The warming continues. The ecological collapses accelerate. The planet is becoming a runaway train, and the hive mind, for the first time in its existence, is beginning to feel a sensation that is entirely alien to it. The cold, creeping logic of impending failure. The very unity that had been their greatest strength was now locking them into a fatal debate, a planetary-scale civil war of competing calculations, while the world they had built began to slowly and silently crumble around them. The internal crisis of the geode hive mind, this logical schism over how to manage their self-inflicted problems, could not have come at a worse time. A civilization is never just an island. It exists within the context of its planet, and the planet itself was beginning to go through a profound natural transformation. The long, stable, humid paradise of the Carboniferous period was coming to an end. We are moving into the next geological period, the Permian. On a planetary scale, the continents, which had been scattered, are continuing their slow, inexorable tectonic dance. They are coalescing, crunching together to form the last great supercontinent in Earth's history, Pangaea. The creation of such a massive, unified landmass has a dramatic effect on the global climate. Ocean currents are disrupted, and vast inland areas are now cut off from the moderating, moisture-bearing winds of the sea. The world on its own is naturally beginning to trend towards a drier, more seasonal climate. The era of the endless global swamp is fading. For the geodes, this natural climate shift is a disaster. It is the one variable they cannot control. Their industrial pollution, that slow fever of global warming they had induced, now combines with this natural drying trend, creating a devastating feedback loop. The warming accelerates the drying, and the drying, in turn, reduces the planet's capacity to absorb their carbon emissions. The runaway train is now careening downhill. You stand at the edge of one of the great carboniferous swamps and watch the catastrophe unfold in slow motion. The edges of the forest are browning and receding. The giant scale trees, which require immense amounts of water, begin to die off, their petrified corpses creating ghostly grey forests. The water table drops, and the soggy ground on which their entire ecosystem is built begins to dry and crack. For the geode hive mind, this is an existential threat of the highest order. Their primary food source, the delicate fungal gardens, are threatened by the changing chemistry and humidity. Their primary energy source, the peat and coal beds, become harder to process as the swamps dry out. The delicate chemical balance of the world, the language of pheromones and airborne signals they use to think, is thrown into chaos by the changing winds and rising temperatures. This external pressure shatters the already fractured unity of the hive mind. The logical debate is over. Survival has become the only imperative. The global superorganism breaks apart. The continent-spanning consciousness dissolves into dozens of competing, isolated sub-collectives. The war is no longer one of ideas. It is a physical, desperate conflict for dwindling resources. For the first time in their history, geodes are fighting geodes. It is a civil war on a scale and in a manner we can barely comprehend. They don't fight with tanks and bombs, but with the terrifying tools of their bioengineering. One hive might unleash an engineered plague, a fungus designed to attack the specific crops of a rival colony. Another might deploy a chemical agent that deafens their enemies, severing their connection to their own local hive mind and leaving them as mindless, twitching individuals. They collapse major tunnels, sealing off vast sections of the global network to protect their own territory and starve their rivals. The very infrastructure that had united them, the fungal communication network and the subterranean highways, becomes the battlefield. For a human historical fact that serves as a pale analogy, historians often speak of the late Bronze Age collapse around 1200 BCE. In the eastern Mediterranean, a number of powerful and interconnected civilizations, the Mycenaean Greeks, the Hittite Empire, the New Kingdom of Egypt, all fell into a rapid and catastrophic decline. There was no single cause. It was a systems collapse, a perfect storm of climate change, leading to drought and famine, invasions by mysterious sea peoples, disruption of trade routes, and internal rebellions. It was the end of a world. The geodes are experiencing their own systems collapse, but on a global scale, and with the added horror that the invaders and the rebels are themselves. The great intellectual light of the hive mind has been extinguished, replaced by the frantic, panicked scramble of a dying animal. The geode civilization is tearing itself apart. The great hive mind is shattered, its global network a war zone. Their perfectly managed world is unraveling due to a combination of their own industrial excesses and the planet's natural climate shift. They are a fallen empire fighting over the scraps in the ruins of their own creation. And it is at this moment, with the geodes at their absolute weakest, that the planet prepares to deliver the final apocalyptic blow. We are now going to connect the end of our fictional story to the single greatest catastrophe in the history of complex life on Earth, the Permian Triassic extinction event, also known as the Great Dying. This was not a normal extinction. It was a near-total wipe of the planetary hard drive. Over a geologically brief period of time, life was almost completely extinguished. The culprit, as identified by a mountain of scientific evidence, was not an asteroid from the heavens, but a cataclysm from within the Earth itself. The cause was a massive volcanic event known as the Siberian Traps. In what is now modern-day Siberia, a colossal plume of superheated magma from the deep mantle burned its way through the Earth's crust. When it broke through, it didn't create a single cone-shaped volcano like Mount Fuji. Instead, it triggered immense fissure eruptions. The very ground split open for hundreds of miles, creating curtains of fire that gushed unimaginable volumes of lava across the landscape. This wasn't a one-time event. It was a volcanic spasm that lasted for hundreds of thousands of years, eventually covering an area of 7 million square kilometers, larger than Western Europe, in a thick blanket of basaltic lava. For the warring factions of the shattered geode civilization, this is the beginning of the end. The initial eruptions would have triggered earthquakes of a magnitude they had never experienced, collapsing vast sections of their subterranean world and crushing entire colonies in an instant. But the lava was only the local effect. The true killer was what the Siberian Traps were pumping into the atmosphere. As the magma burned through the thick layers of carboniferous coal and other organic-rich deposits that the geodes themselves had been mining, it released truly biblical quantities of carbon dioxide, methane, and sulfur dioxide into the air. The sky across the entire planet would have darkened with a toxic, volcanic smog. The sun would have been blotted out for years at a time, causing the remaining surface plants to wither and die. The sulfur dioxide would have mixed with atmospheric water to create powerful corrosive acid rain, which would have fallen on the land and oceans, poisoning the soil and dissolving the delicate biological structures of their world. And then came the heat. After the initial cooling from the sun-blocking smog, the immense injection of CO2 and methane, a greenhouse gas far more potent than carbon dioxide, sent the planetary thermostat into a runaway death spiral. Global temperatures soared, perhaps by as much as 10 degrees Celsius on average. The remaining swamp forests, already stressed by the natural drying of the Permian, were cooked into oblivion. This is the point where our thought experiment can take a dark and speculative turn. We are already assuming the geode's industrial activity was pumping greenhouse gases into the atmosphere. This leads to a terrifying question, one that forms a kind of fictional scholarly debate. Scientists still debate whether the geode's atmospheric pollution could have acted as a trigger, destabilizing the mantle plume that led to the Siberian Traps eruption. Could the blanket of greenhouse gases they created have trapped just enough heat in the crust and upper mantle to push an already unstable geological system over the edge? It's a chilling thought, a feedback loop where their own smaller-scale apocalypse summoned an even greater planetary-scale one. In their struggle for survival, did they inadvertently pull the trigger on the gun that would kill the entire world? Whether they caused it or were simply its victims, the result is the same. For the geodes, the world has become hell. The air is poison, the rain is acid, and the planet is caught in a runaway furnace. The surface is now completely uninhabitable. Their great civil war is rendered moot. There is nothing left to fight for. The only imperative now, for the few remaining isolated colonies, is to retreat, to go deeper into the crust than they have ever gone before, and to pray that they can somehow ride out the storm as their world burns and dies around them. The land is a world of fire, acid rain, and choking smog. But the apocalypse unfolding on the surface is only half the story. The oceans, where complex life on this planet first began, are now turning into a toxic, suffocating graveyard. The same mechanisms that are destroying the terrestrial world are now poisoning the seas, creating a catastrophe of a different but equally horrifying nature. The first blow to the oceans is a chemical one. The colossal amount of carbon dioxide being pumped into the air by the Siberian traps doesn't just stay in the atmosphere. The surface of the ocean acts like a great sponge, absorbing vast quantities of it. When CO2 dissolves in water, it forms carbonic acid. You've experienced a very weak version of this yourself. It's what gives carbonated drinks their slight tangy bite. But now, imagine this process happening on a global scale, for thousands of years. The oceans of the world are becoming steadily more acidic. For marine life, this is a death sentence. Countless species of plankton, corals, and mollusks, the very base of the oceanic food chain, build their shells and skeletons out of calcium carbonate. As the water acidifies, this material begins to dissolve. It's like trying to build a house out of sugar in the pouring rain. These creatures, unable to form their protective shells, are wiped out. The entire foundation of the marine ecosystem simply dissolves away. The second blow comes from the heat. As the planet warms, the oceans warm too. And just like a glass of soda left out on a hot day, warmer water cannot hold as much dissolved gas. The gas that all animal life in the sea needs to survive is, of course, oxygen. As the oceans heat up, they begin to suffocate. This process starts at the poles and spreads, creating vast, ever-expanding zones of anoxic water with little to no oxygen. For any creature with gills, like the remaining fish and the last of the once mighty trilobites, this is the end. They are caught between two impossible choices: stay in the shallows and be cooked, or dive deep and suffocate. And it is in these warm, stagnant, anoxic waters that a new and terrifying form of life begins to thrive. With the normal oxygen-breathing organisms gone, the stage is set for anaerobic bacteria to take over. Specifically, a type of bacteria that metabolizes sulfur compounds to survive. As these bacteria multiply in the suffocating depths, they release a toxic byproduct: immense quantities of hydrogen sulfide gas. This is where the horror reaches a truly gothic level. Hydrogen sulfide is the gas that gives rotten eggs their distinct, nauseating smell. The deep oceans are now brewing this poison on a planetary scale. It saturates the deep water, turning it into a toxic purple soup, then begins to bubble up to the surface. The entire world would have smelled like death and decay. For any remaining air-breathing creatures on the shorelines, this gas was a potent neurotoxin, but it gets even worse. For a truly quirky and terrifying tidbit, this hydrogen sulfide gas, once it reached the atmosphere, would have attacked the planet's ozone layer, the delicate shield that protects the surface from the sun's lethal ultraviolet radiation. With the ozone layer shredded, the Earth would have been blasted by hard UV, causing mutations and death in any life that was still somehow clinging to existence. For the last desperate remnants of the geode civilization, this seals their fate. Any surface operations they might have maintained, the vents for their weather control systems, their shoreline processing plants, are obliterated. The acid rain would dissolve their carefully engineered biostructures, and the toxic ozone-depleted atmosphere would make any surface activity instantly lethal, even for their hardened bodies. There is no escape. The planet's entire biosphere, from the deepest ocean to the highest mountain, has become a single, interconnected death machine. Their only remaining option is the one they are forced to take: to retreat. They abandon the upper levels of their vast network, sealing off the passages that lead to the poisoned surface. They sever their connection to the world they once ruled, a world that is now entirely alien and hostile to them. They pull back into the deepest parts of their subterranean realm, huddling around the geothermal vents that were their first source of power. In the crushing dark, miles beneath the scorched and dying surface, the last survivors of Earth's first great civilization brace themselves for a long, seemingly endless night, hoping against hope that the storm will eventually pass. The surface of the Earth is a ghost. The skies are a chemical haze, the oceans are a purple toxic broth, and the land is a scorched ruin. But deep, deep beneath the crust, in the last isolated pockets of their once great empire, the geodes still cling to existence. They are now a civilization of refugees in their own home, trapped in their deepest geothermal sanctums, miles below the apocalypse they fled. The world they knew is gone, a distant memory encoded in their chemical language. All that is left is the darkness, the heat of the Earth's core, and the dwindling hope of survival. But the cataclysm is not just a surface-level event. The Siberian traps are a planetary wound, and the convulsions are shaking the very foundations of the world. The geothermal vents that were once their salvation now become the instruments of their demise. The immense and unending seismic activity from the volcanic eruptions sends shock waves propagating through the crust. Their deep Earth cities, marvels of bioengineering designed to last for eons, are now subjected to stresses they were never meant to withstand. You are with one of the last colonies. The world is a constant low-frequency tremor, punctuated by violent, terrifying jolts. The resin-coated walls of the great caverns begin to crack and groan. Tunnel earls that had connected them to other colonies, now silent for centuries, collapse in thunderous implosions, sealing them off forever. Their power systems, which relied on a delicate and precise network of channels to control the flow of superheated water and steam, begin to fail. A sudden shift in the rock can sever a primary conduit, plunging a fungal farm that feeds millions into sudden, cold darkness. Or worse, a breach can unleash a blast of superheated toxic gas from the mantle, flash-boiling entire chambers in an instant. The greatest tragedy, however, is not the collapse of their cities, but the collapse of their minds. The geode consciousness, the great hive mind, was a delicate, emergent phenomenon. It required constant, stable communication between all its individual units. But now, in the poisoned and chaotic environment of their dying sanctuary, that communication is breaking down. The subtle chemical signals they rely on are being contaminated by strange volcanic gases seeping up from the mantle. The vibrational messages they tap through the rock are lost in the constant thunder of the planetary death throes. The hive mind begins to dissolve. It's the cognitive equivalent of a fatal stroke. Thoughts that once crossed continents in seconds now become garbled, corrupted static. The collective consciousness, the entity that had solved the mysteries of biotechnology and engineered a planet, is now just a confused and terrified whisper in the dark. The individual geode units, for the first time in their evolutionary history, are effectively alone, severed from the great we that had given them purpose. They revert to simple, instinctual behaviors, a chaotic scramble of confusion and fear. The light of their intelligence, arguably the first great intellectual light the planet had ever known, is flickering out. As a historical fact, we can find a faint human echo of this kind of desperate final stand in the fall of Constantinople in 1453. For over 1,000 years, the city had been the capital of the Byzantine Empire, the last remnant of Rome. In its final days, besieged and outnumbered, its citizens fought street by street, defending the crumbling walls of a civilization that was already dead. It was an act of incredible bravery in the face of inevitable doom. The last geode colonies are fighting a similar battle, not against an invading army, but against the very planet itself. A desperate, final defense of a world that has already vanished. But there is no victory to be had. The end comes not in a single fiery blast, but in a slow, suffocating whimper. The last colonies, isolated and cut off, succumb to 1,000 different failures. Some starve as their fungal farms wither from a lack of power. Some suffocate as their air circulation systems fail. Others are simply crushed in the final shuddering collapse of their subterranean world. The billion-year evolutionary journey of their lineage, from a simple arthropod scuttling on the sea floor to a being of planetary consciousness, ends here, alone, in the crushing dark. Their story is over. Their existence is now a secret, kept only by the silent, unforgiving rock. The last geode colony flickers out, and a profound silence falls over the deep earth. The planet's first great experiment with intelligence is over, but the cataclysm that ended their story is just getting started. The Siberian traps continue their violent eruptions for what might be as long as 1,000,000 years. The planet is locked in a state of purgatory, a hothouse hellscape from which it seems there can be no recovery. The great dying is in full swing, and it is methodically, patiently, and brutally wiping the slate clean. The numbers, derived from the stark scientific evidence in the fossil record, are difficult to comprehend. Life on Earth came as close to being completely extinguished as it ever has, before or since. In the oceans, it's estimated that over 90%, perhaps as much as 96%, of all species vanished. The once mighty trilobites, who had survived for 300 million years, are gone forever. The great sea scorpions, the vast and beautiful coral reefs, all gone. On land, the devastation is just as severe, with over 70% of all terrestrial vertebrate species disappearing. The great amphibian predators of the carboniferous swamps are wiped out. The diverse and strange reptile-like creatures of the Permian are decimated. The world has become a ghost of its former self. And in this process of planetary cleansing, the evidence of the geode civilization is being systematically erased and buried. Their great subterranean cities, already collapsed and lifeless, are now being subjected to immense geological forces. Kilometers of volcanic ash and fresh sediment, washed from the barren, eroding continents, pile up on top of them. The immense weight from these new layers, combined with the extreme heat still radiating from the volcanic activity, begins the process of metamorphosis. The delicate bioengineered structures, the reinforced tunnels, the fossilized remains of the geodes themselves, all are being compressed, cooked, and transformed. Organic matter is baked into sterile graphite. Secreted resins and polymers are warped into strange, crystalline veins. The ruins of their civilization are being turned into just another layer of metamorphic rock, their story scrambled into a geological code that is nearly impossible to read. On the surface, the world is being repaved. The massive lava flows from the Siberian traps create a new surface for the planet, a vast, sterile plain of black volcanic rock. The world that the geodes knew, the world of the great coal swamps, is now just a memory, buried under a tombstone of basalt. The stage is being meticulously cleared for the next great act in Earth's long drama. The planet is hitting the reset button in the most violent way imaginable. Yet life, in its incredible tenacity, clings on. In the midst of this global graveyard, a few hardy survivors manage to find a foothold. And one of the most successful, for a truly quirky tidbit of paleontological history, was a creature called Lystrosaurus. It was a synapsid, a distant relative of mammals, and it looked something like a cross between a pig and a lizard, with a stout body, a beaked face, and 2 tusks. It wasn't particularly big, fast, or smart, but it was tough, adaptable, and likely a good burrower, which may have helped it survive the worst of the surface conditions. In the barren, post-apocalyptic world of the early Triassic, Lystrosaurus didn't just survive, it thrived. For a time, this one single genus of animal made up as much as 95% of all land vertebrates on the entire planet. Imagine for a moment a world where almost every large animal you see, from the plains to the hills, is the same pig lizard. That was the world after the Great Dying. A world of disaster fauna, a world starting over with a very limited cast of characters. The complexity and diversity of the Paleozoic were gone, replaced by a strange and impoverished echo. The reign of the geodes was over. The reign of Lystrosaurus had begun. The world of Lystrosaurus is a quiet, empty one. The planet is in a state of shock, its biosphere shattered. But the Earth has a powerful ability to heal itself, given the one thing it has in abundance: time. We now move forward, slowly, through the millions of years that follow the Great Dying. The violent convulsions of the Siberian traps finally cease. The volcanoes fall silent. The atmosphere, no longer being actively poisoned, begins a long and arduous process of recovery. Rain slowly scrubs the toxins from the air. The oceans gradually re-oxygenate and lose their acidity. The runaway greenhouse effect subsides, and the global climate stabilizes into a new, though permanently altered, state. Life, resilient and relentless, begins its slow climb back from the abyss. The few hardy survivors of the extinction emerge into a world of immense opportunity. There are countless empty ecological niches, vast real estate for the taking. The Triassic period, the first chapter of the new Mesozoic era, is a time of strange evolutionary experiments. As a historical fact, this period was not immediately dominated by the dinosaurs. It was a chaotic scramble for power. Strange crocodile-like reptiles called Rauisuchians became the apex predators on land. Bizarre, hippo-like amphibians called metaposaurs crowded the rivers. And the synapsids, the lineage that includes Lystrosaurus and our own distant ancestors, were making a comeback with creatures like the fearsome, saber-toothed Gorgonopsians. It was a weird, transitional world, a biological Wild West. But among all these contenders, one group of reptiles, small and unassuming at first, possessed a few key advantages, perhaps in their breathing, their metabolism, or their posture. They were the dinosaurs. And over the course of the Triassic, they slowly but surely outcompeted their rivals. By the time another smaller extinction event at the end of the Triassic cleared out many of the other strange contenders, the dinosaurs were perfectly positioned to take over. They rose to a position of dominance that they would hold for the next 150 million years. They became the undisputed masters of a world that had absolutely no memory of what had come before them. The age of the geodes was ancient, forgotten history. The age of the dinosaurs had begun. And what of the geodes? What is left of their million-year empire? They are now nothing more than a ghost in the machine, a subtle anomaly in the rock. Their story has been translated into the silent, cryptic language of geology. Their vast, bioengineered cities, crushed and cooked deep in the crust, are now just warped, mineralized veins of quartz and calcite, indistinguishable from natural formations to all but the most perceptive eye. Their carefully managed forests, compressed by time and pressure, have become unusual and chemically strange seams of coal and graphite. Their countless trillions of bodies, fossilized and then metamorphosed, have been rendered into smears of carbon in the stone. And their great industrial legacy, the fingerprint they left on the entire planet, it's almost gone. Their carbon isotope excursion is now just a faint, anomalous spike in the data, one of many strange blips in the chaotic chemistry of the Permian-Triassic boundary. The microscopic plastic-like polymers they created have long since broken down, leaving behind only a subtle and confusing layer of complex hydrocarbons. Their engineered life forms have been erased, their legacy buried by 250 million years of subsequent evolution. All that is left of a civilization that commanded the planet is a handful of ambiguous, circumstantial clues spread across a thin, dark line of clay in the rock. A geological whisper so faint it is almost impossible to hear over the background noise of the planet. Their story is well and truly over. They are gone. And for the next 250 million years, the planet will get on with its business. The dinosaurs will rise and fall. The continents will break apart. The mammals will have their chance. And one of them, a clever primate on the plains of Africa, will learn to use tools, and then fire, and then language. It will build its own civilization, one that will eventually develop the tools and the curiosity to look back into the deep past, to drill into the rock and read the faint chemical signatures. 250 million years after the last geode colony perished in the dark, our story, the story of the search, finally begins. The time machine comes to a halt. The long journey back through the eons is over. You are no longer a passive observer in the deep past. You are back in the present day. The air is a comfortable 21% oxygen. The sun is its familiar, friendly brightness. And you are a scientist, a geologist, perhaps a paleontologist or a geochemist. And you are standing in the dry, dusty heat of the Karoo Basin in South Africa. This place is one of the most important locations on Earth for understanding the Great Dying. The rocks here form a perfect, uninterrupted sequence that spans the Permian-Triassic boundary. It is, for your purposes, a geological crime scene. Before you is a large rock outcrop, a hillside where the layers of time are exposed like the pages of a book. The colors of the rock tell the story. The lower layers, the rocks of the late Permian, are a rich, greenish-gray mudstone, filled with the fossilized bones of the diverse and fascinating creatures that lived here before the cataclysm. This was a vibrant, thriving ecosystem. As your eyes travel upwards, you see a stark, dramatic change. The rich, fossil-bearing rock stops abruptly. Above it lies a thin, dark, almost black layer of clay. This is the boundary. This is the tombstone of the Paleozoic world. There are almost no fossils in this layer. It is often called the dead zone. It is the physical scar of the extinction event, a moment of planetary death captured in the stone. And then, as you look at the layers above that stark boundary line, you see the story of the slow, painful recovery. The rocks of the early Triassic are a reddish, barren-looking siltstone. Life has returned, but it is impoverished. The fossils you find here are almost all of the same creature, the hardy, disaster-loving Lystrosaurus. The rich diversity of the Permian is gone, replaced by a monotonous, low biodiversity world. It would take millions of years for the ecosystems to recover their former complexity. You can see the whole tragedy laid out before you in the rock. A world full of life, then a moment of death, followed by a long, slow period of recovery. You've been here a dozen times. You know this story. The official explanation is the Siberian traps. It's a solid, well-supported theory that accounts for most of the evidence. But something has always bothered you and your small team of fellow researchers. Over the past few years, your lab has been analyzing samples from this boundary layer with new, more sensitive equipment, and you have started to find anomalies. Strange little chemical quirks and microscopic oddities that don't quite fit the neat and tidy volcanic model. They are whispers, inconsistencies, loose threads in the official story. This is why you are back here today. You are not just studying the extinction anymore. You are on a far more speculative and potentially revolutionary quest. You are hunting for a ghost. You are searching for the subtle, almost imperceptible evidence of the geodes. The rest of the scientific community would call you crazy. They would say you are chasing a fantasy, seeing patterns in the noise. The Silurian Hypothesis is just that, a hypothesis. A thought experiment, not something a serious scientist should be dedicating their career to. But the anomalies are real. The data is what it is. And it has led you here, back to this dusty hillside in the Karoo, to look at this familiar boundary layer with new eyes. You run your hand over the rough, dark clay of the dead zone. You know that the Siberian traps were real. You know they were the primary kill mechanism. But what if they weren't the whole story? What if there was another factor involved? What if the extinction was a 1-2 punch? A civilization-induced crisis that weakened the biosphere, followed by a natural cataclysm that delivered the final knockout blow. Your theory is that the faint, strange signals your team has found are the echo of that first punch, the chemical ghost of the geode civilization's collapse, buried within the larger chemical cataclysm of the volcanoes. Today, you are here to collect new, cleaner samples to see if you can finally isolate that faint signal from the overwhelming noise of the extinction. The search has begun. Your expedition to the Karoo Basin was a success. You now have what you came for, a series of deep, pristine sediment cores drilled from a location where the Permian Triassic boundary is perfectly preserved. Back in the clean, sterile environment of your university lab, far from the African heat, you and your small team begin the painstaking process of analysis. The core is a long cylinder of rock, about 4 inches in diameter. It is a time capsule, a high-resolution recording of the single worst catastrophe in Earth's history. Your job is to play that recording back, 1 millimeter at a time, and listen for a voice that no one has ever heard before. The core is sliced lengthwise, one half preserved in an archive, the other destined for analysis. You begin with the big one, the first and most obvious signature, the carbon isotope excursion. Using a mass spectrometer, a machine that can identify the chemical makeup of a sample with incredible precision, you analyze tiny scrapings of dust from each layer of the core. As you plot the data, the expected pattern emerges. Right at the PT boundary, you see a massive, dramatic spike in light carbon isotopes, the clear fingerprint of the Siberian Traps volcanoes pumping billions of tons of cooked carbon into the atmosphere. It's the signature of a world on fire. It's exactly what the textbooks say should be there. But then you see it. You zoom in on the layers just below the main volcanic signature, the rock that represents the last few thousand years of the Permian world, right before the main eruptions began. And there it is. A second spike. It's much smaller, a mere tremor compared to the earthquake of the volcanoes, but it is undeniably there. A brief, sharp, and entirely unexplained release of light carbon into the atmosphere that precedes the cataclysm. The rest of the scientific community has always dismissed this little blip as a statistical anomaly, a precursor pulse from the volcanoes, or some kind of geochemical noise. But to you, it is the first clue. It is the perfect signature of the geode industrial revolution, the echo of them burning through the carboniferous coal swamps. A clear signal of a biosphere being pushed out of balance before the main event. This could be it. This could be the ghost. The excitement in the lab is palpable, but you have to remain skeptical. One piece of anomalous data is not proof of anything. You need more. You move on to the next phase of the investigation. Microscopic analysis. You take a thin slice of rock from that same anomalous layer just before the extinction and place it under a powerful scanning electron microscope. This is where you look for the technofossils, the physical remnants of their industry. Under the intense magnification, the world of the rock becomes a strange, alien landscape. You see the normal, expected things, mineral grains, fossilized fragments of pollen, bits of organic matter. But then you start to find things that don't belong. You find tiny, perfectly spherical particles of carbon. They are not jagged, like soot from a natural fire. They are too uniform, too perfect, almost as if they were manufactured. Could these be the microscopic byproducts of the geode's efficient, low-temperature gasification of coal? Then you find something even stranger. You find thin, tangled filaments of a complex, carbon-based polymer. They look unnervingly like the degraded remains of microplastics. You run a chemical analysis, and the molecules are bizarre, a long-chain hydrocarbon that doesn't match any known natural compound. It's an exhilarating and slightly spooky discovery. There's a strange phenomenon in folklore known as witch's jelly, or star jelly, a quirky name for a mysterious gelatinous substance that is sometimes found on the ground after a meteor shower. While it almost certainly has a mundane explanation, it's usually the regurgitated guts of a frog or the remains of some kind of slime mold. It speaks to our primal fascination with finding strange, unidentifiable materials that seem to have fallen from another world. What you are seeing on your microscope screen is the scientific equivalent of that. It is a material that simply shouldn't be there. It feels alien. It is a second line of evidence, a physical clue that seems to corroborate the chemical clue of the carbon spike. The case is getting stronger. You have two compelling yet circumstantial pieces of evidence: the strange carbon spike preceding the extinction event, and the microscopic plastic-like filaments tangled in the rock. It's enough to fuel your suspicion, but it's not enough to convince a skeptical world. You need more. You need to find other, independent signatures of industry, all pointing to the same thin layer of rock, the same moment in deep time. Your investigation now moves to its next phase, a search for the chemical ghosts of heavy industry. You return to the mass spectrometer, but this time you are not looking at carbon. You are doing a full elemental analysis of the pre-extinction boundary layer, screening for heavy metals and other trace elements. An industrial civilization, even a highly efficient biological one like the geodes, would inevitably have an impact on the planet's chemical cycles. Their mining, their chemical synthesis, their waste disposal. All of these processes would concentrate certain elements in unnatural ways. As the data from the spectrometer begins to scroll across your screen, a new set of anomalies appears. In that same narrow band of rock that contains the carbon spike and the strange polymers, you find unusual concentrations of a whole suite of metals. There are elevated levels of copper, zinc, nickel, and several rare earth elements like neodymium and yttrium. This is a perplexing find. A spike like this is often the signature of an asteroid impact, as meteorites are rich in these kinds of elements. But when you look for the telltale sign of an impact, the smoking gun of iridium that was found at the dinosaur extinction boundary, it's not there. The iridium levels are perfectly normal. So whatever caused this metallic spike, it wasn't a rock from space. It looks less like an impact event and more like industrial pollution. It's a chemical signature that strongly suggests large-scale mining, smelting, and manufacturing. Perhaps the geode's bioengineering required vast quantities of copper for a hemocyanin-like blood, or they used rare earth elements as catalysts in their chemical reactors. This metallic layer is the fossilized waste stream of their civilization, a chemical garbage dump that was spread across the entire planet. This may seem far-fetched, but we have a clear historical fact that proves even pre-modern industry can leave a global trace. Researchers drilling ice cores in Greenland have been able to create a pollution record that goes back thousands of years. In the layers of ice corresponding to the Roman Empire nearly 2,000 years ago, they found a distinct and surprising spike in lead pollution. This lead has been traced all the way back to the Romans' massive silver mining operations in Spain. The smelting process released plumes of lead-filled smoke that were carried by the winds all the way to Greenland, where they settled on the ice and were preserved. If the Romans, with their furnaces and bellows, could leave a detectable fingerprint on the other side of the world, a truly global civilization like the geodes, operating for millions of years, would have undoubtedly left a much, much larger one. This is your third clue. You now have a trifecta of evidence. A chemical signature of energy production, the carbon spike, a physical signature of manufacturing, the polymers, and a chemical signature of resource extraction, the metals. You decide to push for one final piece of evidence, one that could directly point to the geode's unique, biological brand of technology. You turn to the paleontologists on your team, the experts in the fossilized life of the period. You ask them to re-examine the fossilized pollen and spores found in your anomalous layer. The work is tedious, requiring thousands of hours peering through a microscope. For weeks they find nothing unusual, just the expected fossilized spores of the giant ferns and scale trees of the late Permian. But then, one of your colleagues calls you over to their microscope. They have found something. Scattered amongst the normal flora are the fossilized spores of a fungus that has no known relatives. It is utterly alien. Its morphology is bizarre, and its cell walls appear to be infused with tiny metallic granules. When you run an analysis on the granules, you find that they are composed of the very same heavy metals you detected in your spectrometer: copper, zinc, and nickel. This is the fourth and perhaps most stunning clue. It is a fossil of what appears to be a bioengineered organism, a fungus that was specifically designed to seek out, metabolize, and accumulate heavy metals. It's a perfect candidate for a geode bioremediation tool, a living machine they used to clean up their own industrial waste. You have found not just their pollution, but a fossil of the very technology they might have used to combat it. The ghost in the rock is beginning to take shape. You have it. 4 independent lines of anomalous evidence, all converging on a single razor-thin layer of rock that was deposited just before the world ended. You have a story, a compelling narrative of a lost industrial civilization. You've checked and rechecked your data, calibrated your instruments a dozen times, and ruled out every potential source of contamination you can think of. The signals are real. Now comes the hardest part, convincing your peers. You are standing at a podium in the sterile, fluorescent-lit conference room of a major geological society. The room is filled with some of the most respected minds in your field. On the projector screen behind you is a simple, elegant chart summarizing your 4 key findings: the pre-extinction carbon spike, the microscopic polymers, the non-impact metal concentrations, and the bizarre metal-eating fungus. You have just spent the last 45 minutes laying out your evidence, piece by painstaking piece. Now you open the floor for questions, and you know exactly who is going to speak first. It's a respected older geologist, a man who has built his entire career on the standard model of the Permian Triassic extinction. He stands up, a look of profound skepticism on his face. This is the moment the scholarly debate becomes real. The skeptic begins to speak, his voice calm and measured, and he systematically attacks each one of your points. "This is fascinating work," he begins, a classic academic prelude to a complete dismantling. "But you are making an extraordinary claim, and your evidence is, frankly, nowhere near extraordinary enough. Let's look at your so-called signatures. The pre-extinction carbon spike? We've known about that for years. It is far more likely to be a result of the initial, smaller-scale volcanism that preceded the main Siberian Traps flood basalts. It's the planet's crust starting to crack and cook the coal seams from below. A natural explanation," he continues, pointing at your second piece of evidence. "Your microscopic polymers and spheres? The Earth is a complex chemical factory. Unusually formed fulgurites, created by lightning strikes in carbon-rich soil, can create glassy, spherical structures. Natural hydrocarbon seeps can produce complex, oily polymers that could easily be mistaken for something artificial after 250 million years of heat and pressure. You are seeing industrial plastics where there are only natural tars. As for your metal ratios," he says, warming to his argument, "the lack of an iridium spike simply rules out a single type of asteroid. It doesn't rule out other extraterrestrial or terrestrial sources. A shower of cometary dust, or more likely a period of intense deep ocean volcanic vent activity, could easily dredge up these exact metals from the mantle and distribute them globally without a corresponding iridium signature. And your metal-eating fungus? That's an interesting find. A new species for the books, perhaps. But to leap from an unusual fossil to a claim of genetic engineering by a lost civilization, that is not science. That is science fiction. You are seeing a pattern that simply isn't there. This is all just a series of fascinating but unrelated geological coincidences." The room is silent. He has presented a powerful, logical, and entirely plausible rebuttal. Every one of your clues has a potential natural explanation. Now it is your turn to respond. You take a breath. "You are absolutely correct," you begin, surprising him. "Each piece of this evidence, viewed in isolation, is ambiguous. Each clue on its own could absolutely be dismissed as a geological coincidence. I cannot, with 100% certainty, disprove any of the alternative explanations you've just offered. But the central question is not about the ambiguity of any single piece of data. It is about the staggering improbability of all these coincidences happening at the exact same time, in the exact same thin layer of rock, all across the globe. What are the chances of a precursor volcanic pulse, and a strange hydrocarbon seep, and a period of unusual deep-sea venting, and the evolution of a bizarre metal-metabolizing fungus all occurring in the same geological instant? At some point, the sheer number of coincidences requires a more elegant, more parsimonious explanation. You click to your final slide. The story these clues tell, when viewed together, is a consistent one. They point to a global event that involved massive-scale energy production, the creation of artificial polymers, the industrial-scale use of heavy metals, and even a potential attempt at bioremediation. This is the precise sequence of signatures we would expect to find from an industrial civilization. So yes, it is an extraordinary claim. But the Great Dying was an extraordinary event. Perhaps it's time we considered that it might have had an extraordinary cause. You finish, and the room remains errant. You haven't won, but you haven't lost either. You have opened a door to a radical new possibility. The conclusion, for now, remains uncertain. The scientific method demands more evidence, more testable predictions, but the very nature of deep time, the great planetary eraser that has so thoroughly wiped the slate clean, means that this handful of ambiguous chemical ghosts might be all the evidence that is left. The ghost in the rock has shown itself, but it is still just a whisper, a question mark hanging in the vast silence of geological time. The debate in the conference hall fades away, leaving you with that profound sense of uncertainty. The evidence is tantalizing, but it is not and may never be conclusive. The ghost remains a ghost. So, for a moment, let's step away from the rigorous demands of the scientific method. Let's leave the world of testable hypotheses and hard data and allow ourselves to drift into the realm of pure, unadulterated speculation. The entire exercise has been a thought experiment, after all. Let's push that experiment to its most imaginative and science-fictional limits. Let's ask the question, what if they survived? We watched the last geode colonies perish in the dark, crushed and suffocated by the dying planet. Their extinction seemed total, absolute. But life is tenacious. And a civilization as advanced and powerful as theirs, with a collective intelligence that had commanded a planet for millions of years, might have had one last trick up its sleeve. What if a tiny, isolated remnant of the great hive mind, a single ark colony, managed to endure the Great Dying? Where could they be now? One possibility is that they went deeper. They were already masters of the subterranean world. Perhaps, in their final desperate act, they used their bioengineering to adapt to an environment even more extreme than the one they were used to. Could they have found a way to survive in the Earth's upper mantle itself? Could they have become a species of molten rock, a creature of magma and pressure, their consciousness encoded not in chemicals, but in the subtle vibrations of seismic waves? It's an almost absurdly alien thought, that of a civilization swimming in the very fire beneath our feet, but in a universe of endless possibilities. Who is to say what the absolute limits of life are? Or perhaps they chose the opposite route. Perhaps, seeing that the Earth was a lost cause, they looked to the stars. A civilization that had mastered biotechnology might not need to build great metal starships. Why not engineer life itself to make the journey? This leads us to a fascinating, quirky scientific theory called panspermia. This is the idea that the basic building blocks of life, or even simple organisms like bacteria, could travel between planets, hitching a ride on meteorites blasted into space by ancient impacts. Life on Earth, in this view, might have been seeded from Mars, or even from another star system. What if the geodes took this natural process and perfected it? What if their final act was to encode the totality of their genetic makeup and collective consciousness into a set of hyper-durable radiation-resistant spores? They could have then launched these spores into space, a final desperate message in a bottle, trusting that one of them, millions of years later, might land on a new, hospitable world and reawaken the hive mind. Perhaps the geodes are out there, right now, thriving under the light of a distant star, the ancient ancestors of a new galactic empire. But there is a third, and perhaps more unsettling possibility. What if they never left, but simply hid their legacy? They would have known that their world was ending, that a new age of simple, brutish life would follow. They would have also known that, given enough time, evolution might once again produce an intelligent, tool-using species. They might have wanted to leave a message for us, their unlikely successors. But how do you leave a message that can survive for 250 million years of geological chaos? Not on a stone tablet, not even on a golden record sent into space. You leave it in the one place that is guaranteed to survive: life itself. Imagine if the geodes, in their final days, captured a simple, common, and incredibly durable life form, like a bacterium. And into the junk DNA of that bacterium, they encoded a message. A history of their civilization. A warning about the dangers of unchecked industrial growth. Perhaps even the secrets of their biotechnology. They could then re-release this bacterium into the dying world, knowing that it would survive, multiply, and evolve, its descendants spreading to every corner of the globe. The message would be carried, dormant and unseen, through the age of dinosaurs and the rise of mammals, a secret passenger in the genetic code of life itself. And it would be there, still, today, inside the soil, inside the oceans, perhaps even inside of you, waiting for a civilization with the technology to read the deepest secrets of the genome, to finally discover it. The ghost in the rock could be a pale shadow of the ghost in our own cells. It's the ultimate science fiction trope, but it's a powerful and thought-provoking one. The greatest secret of all might not be buried in the past, but hidden in the present. The idea of a secret message in our DNA, or a civilization of magma beings in the mantle, is a wonderful, dizzying fantasy. It's the kind of speculation that makes science fiction so captivating. But now it's time to pull back from the edge of imagination and return to the solid ground of the present. It's time to bring this entire story home. Because the true value of the Silurian Hypothesis and the story of our fictional geodes is not what it tells us about the deep past, but what it reflects back at us about our own present. The entire thought experiment is a mirror. The story of the geodes is a cautionary tale, a planetary-scale fable for our own time, the Anthropocene. Think about the arc of their story. They began as a species in relative balance with their world, powered by a sustainable energy source in the form of geothermal heat. Then, they discovered a new, incredibly dense, and seemingly limitless source of power buried in the ground. Fossil fuels. This new energy source allowed for an unprecedented explosion in their population, their complexity, and their technological power. They reached a golden age, becoming a truly global force, even developing the ability to engineer the planet's climate and its biosphere to suit their needs. But their success came at a cost. Their industrial processes began to alter the fundamental chemistry of the planet's atmosphere and oceans. Their planetary engineering had unforeseen consequences, destabilizing the very ecosystems they were trying to control. They became aware of the problem, and a great debate began within their collective mind, a conflict between those who advocated for a retreat to a more sustainable model, and those who believed the only solution was more and better technology. And while they were locked in this internal conflict, their pollution, combined with a natural climate shift, pushed their world past a tipping point, leading to a runaway systems collapse and, ultimately, their own extinction. Does any of that sound familiar? It should. The parallel is so direct, it is almost painful. We too began as a species in relative balance with our world. We too discovered the immense power of fossil fuels, and it too launched our own industrial revolution and a golden age of technological and population growth. We too have become a geological force, altering the planet's chemistry and debating our ability to engineer the climate through geoengineering. And we too are now acutely aware of the consequences of the slow-building fever of the planet and the destabilization of our ecosystems. We are, right now, living through our own great debate about sustainability versus technological solutions. The story of the geodes is our own story, told with a different cast of characters. And the parallels don't end with the narrative. They are written in the rock. The very signatures you, as the geological detective, were searching for from the geodes. The carbon isotope excursion from burning fossil fuels, the layer of microscopic synthetic polymers, the strange concentrations of industrial heavy metals? These are the exact same signatures our civilization is laying down in the sediment right now. We are actively, at this very moment, creating the evidence that some future geologist, 100 million years from now, might use to piece together the story of our own rise and fall. They will find the clear spike in light carbon. They will find the layer of plastic microfibers. They will find the global fingerprint of lead from our gasoline and the strange isotopes from our nuclear tests. We are not ignorant of this. As a crucial historical fact, the very first Earth Day was held in 1970. This event marked a major turning point in public consciousness, a moment when a significant portion of humanity began to understand its own power to damage the planet's life support systems. For over 50 years, we have been aware that we are a geological force, that our own success could be the instrument of our own demise. We know we are creating these technofossils. We know we are writing a new, and perhaps final, chapter in the rock. The story of the geodes serves as a powerful reminder that we are not the first system on this planet to face this kind of crisis, and their silence in the rock is a sobering testament to what happens if you get the answer wrong. The story of the geodes is a mirror, reflecting our own challenges and our own potential geological legacy. But it's also a lens, one that can change the way we look at one of the greatest and most profound scientific questions of all time. Are we alone in the universe? This is the heart of the famous Fermi paradox. The paradox, first formulated by physicist Enrico Fermi, is simple. Our galaxy, the Milky Way, contains hundreds of billions of stars. A significant fraction of those stars likely have planets, and a fraction of those planets are likely in the habitable zone, where conditions could be right for liquid water and life. Given the billions of years the galaxy has been around, it seems there has been more than enough time for intelligent, technological life to have evolved, not just once, but many times. So, as Fermi famously asked over lunch one day, "Where is everybody?" For over half a century we have been listening. We have built colossal radio telescopes, sensitive dishes pointed at the heavens, straining to hear a single, structured, non-natural signal from the cosmic static. This is the project known as SETI, the Search for Extraterrestrial Intelligence. And so far, in all that time, from all those billions of stars, we have heard nothing but a profound and deafening silence. This is often called the Great Silence. There are many proposed solutions to the Fermi paradox. Perhaps life is incredibly rare. Perhaps intelligence is an evolutionary fluke. Perhaps interstellar travel is simply impossible. Or, in a more ominous line of thinking, perhaps there is a great filter, some inevitable challenge that all civilizations face, and that none, or very few, ever manage to overcome. They might destroy themselves in nuclear wars, or succumb to engineered plagues, or, as in the story of the geodes, their own industrial success might trigger a planetary collapse from which they cannot recover. But the Silurian Hypothesis, our journey into Earth's deep past, offers a new and perhaps more unsettling perspective on the Great Silence. It forces us to ask a question that is both more intimate and more profound. What if we can't even be sure we are the first intelligent life to have evolved on our own planet? We look to the stars, scanning distant solar systems for the techno-signatures of an alien civilization, things like industrial pollutants in their atmospheres, the heat signature of a planet-spanning city, or the radio waves from their communications. We are, in effect, looking for the galactic equivalent of the chemical ghosts we were searching for in our own rock strata. But our entire thought experiment has been an exercise in demonstrating just how fleeting those signatures can be. We have seen how a planet's own natural geological processes are a powerful and relentless eraser of history. We have seen how a global industrial civilization could exist for millions of years, command the resources of an entire world, and then vanish so completely that the only traces left behind are a handful of subtle, ambiguous chemical anomalies that are almost indistinguishable from natural background noise. Now extrapolate that to a galactic scale. If this is what happens on our own world, a planet we can study in intricate detail, what hope do we have of spotting such faint traces from a distance of dozens or hundreds of light years? The cosmos could be a vast cosmic graveyard, filled with the ruins of countless dead civilizations, and we would be completely oblivious. The light we are seeing from a star 1,000 light years away is 1,000 years old. We could be staring right at a planet that, today, is home to a thriving technological empire, but we would be seeing it as it was a millennium ago, long before their industrial revolution. Or more likely, we could be looking at a planet that had a great civilization 100 million years ago, but all that is left is a faint chemical scar that is utterly invisible to our telescopes. The Great Silence, from this perspective, might not be an absence of life, or even an absence of intelligence. The Great Silence might be the sound of geology, of planetary science, working its patient, inevitable magic across billions of worlds. It is the sound of erosion grinding down mountains and alien cities. It is the sound of plate tectonics subducting continents and their histories. It is the sound of mass extinctions, planetary reset buttons hitting world after world. The silence we hear from the stars might be the same profound silence we find in the deep rock layers of our own Earth. The quiet, rustling sound of a library where the books are constantly and inexorably turning to dust. It is important, as we near the end of our long journey, to state one thing with absolute clarity. There is no evidence for the geodes. There is no recognized scientific proof of any industrial civilization on Earth before our own. The strange carbon spike, the anomalous metals, the microscopic polymers, these are all dramatizations, fictional discoveries within our thought experiment. The geodes are a story, a speculative fiction woven into the gaps of the fossil record and the ambiguities of the geological strata. You will not find them mentioned in any geology textbook. They are, for now and likely forever, a fantasy. But the fact that they are not real does not mean that they are not important. The entire purpose of this journey, the true value of the Silurian hypothesis, is not in finding a definitive answer. The value is in the asking of the question. The act of seriously considering a civilization before our own is an exercise in perspective, a mental tool for recalibrating our understanding of our own place in the world. It is a journey that matters not for its destination, but for the vistas it reveals along the way. Asking the question, what if we weren't the first? Forces us to truly comprehend the scale of deep time. It's one thing to hear the number 4.5 billion years. It's another thing entirely to journey through those eons, to stand in the alien landscapes of the Cambrian and the Carboniferous, and to see for yourself how entire worlds can rise and fall, how oceans can be born, and mountains can be ground to dust. It transforms an abstract number into a visceral feeling, a profound appreciation for the immense, almost eternal, stage upon which our own brief story is playing out. It instills a sense of awe for the sheer endurance of the planet itself. Asking the question also forces us to consider the long-term consequences of our own actions in a new and powerful way. When we think about our legacy, we usually think in human terms, in terms of the next generation, or the next century, or the future of our nation. But when you start to think in geological time, you have to ask a different kind of question. What will be the story of humanity as told by the rocks? 10 million years from now? What will our signature be? Will it be a brief, chaotic spasm of strange chemicals and plastic fossils, followed by the silence of a mass extinction? Or will it be the beginning of a long and stable new epoch, a time when a species learned to become a wise and careful geological force? It reframes our current struggles with climate change and pollution, lifting them from the noisy arena of politics and economics, and placing them on the vast, quiet canvas of planetary history. And finally, asking the question cultivates a sense of cosmic humility. It is so easy, so natural, for us to assume that we are the center of the story. We are the pinnacle of evolution, the first and only beings on this planet to look up at the stars and wonder about our place in them. But what if we aren't? What if we are just the current chapter in a much longer book? What if our entire civilization is just a brief flicker of light between two long, silent nights? This thought is not meant to be depressing. It is meant to be liberating. It frees us from the arrogance of assuming we are the most important thing to have ever happened. It connects us to a history that is immeasurably larger than our own. In 1990, at the request of the astronomer Carl Sagan, The Voyager 1 spacecraft, as it was leaving our solar system, turned its camera around one last time and took a picture of Earth from a distance of 6 billion kilometers. The resulting image, a now famous historical fact, is the pale blue dot. In it, the Earth is a single tiny pixel, a mote of dust suspended in a sunbeam. Sagan wrote that this image underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. It was a tool for perspective, a way to humble our sense of self-importance. The question of a civilization before our own is a kind of pale blue dot for time, just as Voyager's picture was for space. It shows us our own time as a tiny, fragile speck in the vast, deep ocean of the past, and in doing so, it encourages us to be better, wiser stewards of the brief, precious moment we have. And so our journey comes to an end. We have traveled from the sun-drenched rim of the Grand Canyon, down through the dizzying abyss of deep time. We have walked on the barren, alien continents of the Cambrian and pushed our way through the humid, monstrous swamps of the Carboniferous. We stood as silent witnesses to the rise of a vast and powerful intelligence, a civilization of beings so different from us, their consciousness a collective hum in the deep earth. We watched them engineer their world into a paradise, and we saw that paradise curdle into a self-inflicted crisis. And we stood by, helpless, as the planet itself delivered the final fiery coup de grace, erasing them in the greatest dying the world has ever known. We have seen how a planet is not a static library, but an active, churning, ever-changing machine that is constantly working to erase its own memory. We have seen how a history, even the history of a globe-spanning empire that lasted for millions of years, can be crushed, cooked, and compressed until all that is left are the faintest whispers, the barest of circumstantial clues. Ghosts in the stone. Our search for the geodes, our speculative dive into the rock, has shown us that absence of evidence is not necessarily evidence of absence. It is, more often than not, simply the natural state of things. The universe does not keep meticulous records. So the next time you are out in nature and you see an old rock, a cliff face layered with different colors, or a great grey mountain, perhaps you'll see it a little differently. Don't just see a lump of stone. See a book with 1 billion pages, where almost all of them have been ripped out, burned, or rendered into a language we can no longer read. See a library filled with the stories of lost worlds and forgotten ecosystems. And understand that you, right now, are a part of the story that is being written in the newest, freshest layer. Our cities, our farms, our plastics, our carbon, all of it is settling into the sediment, becoming the raw material for the technofossils and chemical signatures that will tell our story to the far, far future. The story of the geodes is a tragedy, but it is also a lesson. It reminds us that intelligence is not a guarantee of permanence. It shows us that even the most powerful civilization is still just a thin, fragile film of life, entirely dependent on the stability of the planetary systems that support it. And it urges us, in its silent, ghostly way, to be a civilization that learns from its mistakes, that sees the warning signs, and that chooses a wiser path. It encourages us to write a long and interesting chapter for ourselves, one that does not end in a thin, dark line of ash and silence. And now the time for our journey is truly over. The questions and the mysteries of the deep past can be put to rest for the night. The ghosts in the rock can return to their long slumber, and so can you. The hum of the great planetary machine is fading now, becoming a gentle, soothing drone. The immense pressures of geological time are easing, leaving only a sense of calm and quiet. Let the images of those ancient worlds now soften and dissolve. The strange fern-like trees of the Carboniferous fade into a gentle, blurry green. The dark subterranean cities of the geodes dissolve back into the quiet earth, their faint, glowing lights dimming, one by one, into a peaceful darkness. The great, slow turning of the continents slows to a stop, and the planet is once again still and silent, hanging in the velvet blackness of space like a familiar, peaceful ornament. All the drama and the chaos of deep time, the extinctions and the eruptions, have passed. All that is left is a profound sense of peace, the quiet that follows a long and epic story. You can feel the weight of those millions of years lifting from your shoulders, replaced by the gentle, comfortable weight of your own blanket. Every breath you take is slow and easy, filling you with the calm, familiar air of your own time in your own quiet room. There are no more mysteries to solve tonight. There are no more catastrophes to witness. There is only this moment, this quiet stillness, this gentle descent into a comfortable and well-deserved rest. The story is over, and it is time for sleep. The ghosts of the past are silent, and the dreams of the present are waiting for you.